Thank you. Thank you very much. So this is AI for everyone. So you cannot be in the wrong place. Okay, this is literally the place where everyone is actually welcome. So let's begin. So before I begin, I do wanted to say that so please do sign in to the app and use whatever the code that you see before, so that you could rate it and tell me how stupid I look or things like that sorts. Okay. So, and with that, I just wanted to begin with a short disclaimer. So let me just give you a little bit of a background why this session came to be about. Because throughout my graduate career, I actually been using essentially machine learning to model the human brain. So if you look in my bios or something, I was a neuroscientist. I study how the brain works. And then when I come into the industry, I basically are using my own brain to study how machine learning and AI actually work. So I kind of came full circle. This is using human intelligence to study artificial intelligence, and using artificial intelligence to model human intelligence, and so on. So basically, I've come to the conclusion that basically anyone can actually learn anything they want. It's really a matter of spending the time and effort to do it. I was having a conversation with a UC Berkeley professor. He basically challenged me. He's like, well, I mean, there's so much going on in AI, but there's a lot of people who don't have the technical background. They are totally inaccessible to these topics. And I said, well, I don't think so. I think anyone can do it, because I've basically, from studying machine learning, I basically come to the conclusion that machine can also pretty learn anything they want, given enough data and training, right? So if a machine could do it, why couldn't we do it? So he challenged me to create a course for non-technical people, MBAs, lawyers, doctors, whatever, who doesn't have technical machine learning or statistics background, but who wanted to learn about AI. So basically, I created a 30 hours of course content at UC Berkeley, and so that was actually created for Berkeley Global, and so this is just about 3.5 hour snippet of that course. Okay, I'm not supposed to give the whole course anywhere else besides Berkeley, but if I take 3 hours out of a 30-hour kind of course, I think it's fine. So that's how this course came about. Okay. So let me just begin with a couple of examples of the power of big data. So most of you probably have heard of this example, right? This example is of Target, right? So anybody can read this? If you squint, you can read it. Right? So turns out Target is able to figure out when young women are pregnant before their parents know about it, okay? So now that's actually a little bit creepy, right? So it turns out that they actually do that. I would say there's a little bit of failure in their strategy and what they do with that. But the important thing to realize is that what kind of data do you think Target actually have? They basically have transaction data, right? Transaction data that's like basically who bought what, when, where, how much, quantity, payment methods, and so on, right? These are very typical transaction data. But the information and the insight they get out of that transaction data is that if you actually start buying, these kind of minerals, and you're actually switching from switching to unscented lotions and soaps, then it's an indication that you are pregnant, okay? So obviously, this is a useful insight, but what did they do with that insight? They actually decided to create a coupon book for mommies, and that's where I would say the creepiness came in, right? So basically, they send these coupon book for mommies to someone, and then the dad of the young woman said, like, why are you sending my daughter all this mommy stuff? And my daughter is not pregnant, And then guess what? A couple weeks later, the dad came out and apologized, said, sorry, my daughter is pregnant. Right? So this is actually, I would say, a failure in their strategy. So what they really need to do is simply to create a normal coupon book, just any Target coupon book, and just insert more mommy stuff in there. That's it, right? And that's what they did afterwards, right? And they actually was able to drive significant, I would say, revenue lift from that. So that's one example I want you to keep in mind, okay? Another example is this example of Zest Finance. How many people here heard of Zest Finance? Nobody. Okay, so anyway, so Zest Finance is an online lending platform. So basically you go online, fill out your application, how much money you want to borrow, and then they'll decide, how much whether they want to lend you or not, if so, what the interest rate is, okay? So what kind of data do you think Zest Finance have? What do you think they have? Basically, page after pages of online application, right? Right? That's what they're collecting data to process their loan, to underwrite for whether to give people a loan or not, right? However, the information and the insight that they figured out is that if you fill out this online application with only uppercase or only lowercase, you're more likely to default. Okay? Surprise? Anybody believe that? Okay? I mean, nobody believed that. Even Zest Finance themselves didn't believe it. Okay? But what they did is that they said, okay, I didn't believe it, but I saw some interesting phenomenon here. So what they do is that they actually use this proper capitalization, this data point, right, to augment their traditional underwriting regression model. And guess what? It helps. Okay, it did help. So in this case, so they actually discover a lot of these, I would say, unexpected, features. We call them, later on you'll learn what feature is, so these variables, okay? And there's lots and lots of these that they discover, and they're totally unexpected. Why would these, feature correlated to have anything to do with people's kind of default rate or the ability to pay back a loan, right? They discover a whole bunch of these things, and then they actually tested a lot of them. And it turns out, this one, it actually is making a difference, right? So obviously, this actually makes a huge difference in their business as well, right? So they actually be able to, lower their default rate by 40%, and gain a much bigger market share. Because now, for banks who say like, hey, I can't, lend you money because you're too risky, they say I could lend it to you because I could predict your default rate much better than those banks do. Okay, so very significant result here. So no doubt, data science, machine learning, AI is very, very powerful, but there's also a lot of myth. Lots of myth going on. So one of the myths that I often hear is that people believe that if you actually have a lot of data, you're going to get a lot of information, and you're going to get a lot of insights. Okay, so it makes sense, but this is actually not quite true. Okay, so it turns out that data actually have a lot of what we call statistical redundancy. So anybody can tell me the difference between data and information? Anyone here? No one wants to take even a guess? All right, come on. All right, so think about this. You all have a computer at home, right? Come on. Yeah, okay. And your computer have a hard drive in it, right? And your hard drive have data in it, okay? And those data contain some information, right? So now think about what happened when you back up your hard drive. You just double your data, right? Did you double the information? No, right? So the simplest way to look at the difference between data and information is basically what the data is able to tell you. Think about it that way, okay? What the data is able to tell you, okay? So if you had two copies of the same thing, it's not able to tell you anything more. Okay, so now this is, I would say, duplication is the most trivial kind of, I would say, these are statistical redundancy, right? So there's actually a lot of other reasons why data are very redundant, right? For example, even if I just take my camera here and take a picture right here of all of you, right? And I go back there and ask someone to take a picture from the back of the room, right? So these two pictures look nothing like each other. But there is something that I could tell, from this picture about what the other picture is telling me, right? For example, I could tell approximately how many people are in the room, what clothes are they wearing, how many, so I could tell a lot of things. I could, so it's able to, if I'm able to tell, if one picture is able to tell me some information about the other picture, right? Then they are what we call, there is some statistical redundancy there, okay? Because they're able to tell you the same thing. They're able to tell you the same information. There is this statistical redundancy, okay? So now, there's actually lots of reasons why data are spatial, are kind of have these statistical redundancy, right? So one is spatial temporal correlation. And so the other one is causality, right? Things are causal, right? You can't be, you have pushed this podium, it's going to fall, right? So I'm not going to do that. So turns out the data that's actually not statistically redundant is where the information is. That's the new thing it's able to tell you, okay? Those are the new information that's able to tell you because they're not statistically redundant, right? So now, if you actually go in and extract all the information from those data, turns out a lot of those are actually not insightful. Very often it is the case that if you ask any data scientist among you, that you will, when you actually extract information from data, what you end up with is information you already know. It's just confirming what you already know rather than telling you something you didn't know before. Okay, so that's not insightful, right? So if I tell you that people's income level and their kind of whatever their spending habit is correlated to their default probability, is that insightful? No, because you already know that, right? But if I tell you people's propensity to properly capitalize, that is correlated to their default rate, that is insightful because you didn't know that before, right? Okay, so now. So what criteria must we have in order to have insight? So insights obviously have to be interpretable. The second criteria is it has to be relevant, okay? So the third is that it has to be something new, something that you don't already know, right? So when I talk about this, a lot of people understand what interpretability means, and people know what novelty means. Okay, but very often people have a misunderstanding on what relevance is all about. Okay, when I say relevance, what comes to mind right away? What comes to mind right away? I want to make, hey, so let me just tell you, so I will produce a PDF copy of these slides for you guys. So don't worry about taking notes. I want you to listen, think, and interact, because that's how you learn the best way to learn, okay? And you actually retain a lot of the knowledge a lot better that way, okay? So don't worry about taking notes, okay? So what comes to mind when you talk about relevance? What? Useful, right? Usefulness is actually the thing that most people come up with, right? If something's irrelevant, it's not useful, right? Makes perfect sense. But the problem is that, usefulness is actually, depends on who you're talking to, right? So we'll talk about that concept a little bit. So these information that is now already known, the new information is actually the insight, right? So now let's talk about relevance again, right? So relevance data basically comes to the concept between signal and noise, right? So by definition, signal is the data, the information, the insight that are relevant, okay? By definition, okay? And the rest of it is just noise. The rest of it is noise, okay? Now, the problem is that relevance depends on who you're talking to, right? Usefulness depends on who you're talking to, right? There's actually a famous astronomer that says one man's signal is another man's noise, right? So for example, right, this wedge of data, information, and insight may be relevant to me, right? This may be relevant to you, right? I mean, obviously we have some overlap here because you guys are all here. You guys are interested in learning about AI and machine learning, right? So we have some overlap. But there are a lot of things that may be useful and relevant to you that's completely irrelevant to me, and vice versa, right? So it also depends on, for example, when, right? For example, also depends on where, right? For example, if I'm traveling to Sydney, then the weather there is obviously very relevant to me, right? So I need to get to places, and I'm a foodie, so all the restaurant ratings and reviews there is very relevant to me because I want to make sure that I find the good places to eat, right? But after I come back from that trip, those things are no longer relevant to me anymore, right? No longer relevant, right? So how do you encode these contexts, right? So we said relevance is context specific, right? Depending on your context, what's relevant and what's irrelevant is different. So how do you encode that context? So that context is actually encoded in the question that you're trying to answer, okay? And the problem that you're trying to solve, basically. Okay, so what that means is that if you and I are trying to solve the same problem, okay, or answer the same question, then the relevant data, information, insight to you will be the same as those for me. Okay. However, if you and I are trying to address different problems, different questions, right, then what's relevant to you and I may not necessarily be the same. They may still be the same by chance, but they're not necessarily the same. Okay? All right. So now, big data is noisy, right? How many people here are data scientists? I'm sure there's some people here. There's some people here are data scientists, right? So if you work with big data, you know that big data is actually very, very noisy. The question is why? Why is it so noisy? Okay, so to answer this question of why big data is so noisy, we have to understand how people use data before they were big data. Obviously, people use data before they were big data, right? So how do people use data before we have big data? So you start with the question, right, with the problem. And then what do? You go and collect data to address these questions, right? That's how people, if you've been through, graduate study or something like that, in the last decade, that's how you do science, right? So, and then, if you remember what I said about relevance of data, right? Because this data is collected specifically to address this question, therefore, by definition, they're all relevant, right? By definition, they're all relevant, right? So, in fact, pretty much most of it will be relevant. Now, what happens when you actually have big data? Basically, big data enable data capture to be very, very economical, very, very cheap, right? So now you can actually go collect whatever you want, right, before you even have a question, right? Okay? So now what happens when you actually do have a question, right? So this data, keep in mind, is collected irrespective of any problem that you're trying to solve, right? So when you actually do have a problem, what happened? What happened? Right? Because this data is not collected specifically to address this, right? So most of it will be irrelevant, right? That's why big data is so noisy, right? In fact, these consulting companies have analyzed a lot of these enterprise and realized that the utilization rate of these big data is extremely low, less than 1% typically, okay? So why do you think companies keep all this data around, even though so little of it will be useful or relevant? Yeah, because you don't know what will be useful tomorrow, right? It's context specific, remember? Context depends on who, depends on when, depends on where, right? You don't know. You may not find it useful for it today, right? But you can't guarantee that there is no use for it tomorrow, right? That's why. But moreover, what do you need to do if you have this data, when you have this question now? The first step that data scientists do is basically they just filter out the irrelevant data. Right? Because remember, you collected a lot of data irrespective of what the question is, so now you have a lot of questions. So a lot of these will be irrelevant. So what do? You filter them out. Right? So what's remaining is able to address this problem. Like, keep in mind, this process of filtering the irrelevant data out, it's very, very fast. Okay? Very, very fast. It takes, I don't know, half a day or a couple of days the most, right? And what happened when you actually, if it was the other case? If you have a problem and you don't have the data, how long do you think you're going to be able to collect those data? Sometimes it may be years, right, before you can answer that question, right? In business, that's a death trap, right? Maybe you're done, right? If you actually, if you need to collect data, right, when you actually have a problem, you finish, right? So that's why, even though this actually utilization rate is so low, it's still much better to actually keep these data around because, it's easy to filter out the irrelevant data and it's also much faster if I have a problem coming up, right? So that I can answer those questions, those problems. Okay, so one of the biggest, most common question that I get asked, it's very, very dry here, so I'm going to be periodically drinking water, so I haven't got acclimatized to the Denver altitude here. So anyway, so one of the questions that I get asked most frequently is, where do you look in your big data to find the insights? Right? Anybody have that question asked them? Where do everybody, is telling me that I have tons of data, right? But where do you find the insights? So it turns out, let's look back at this relevant signal, right? Versus noise, right? So by definition, everything in here is relevant. Everything outside is irrelevant, okay? So where should you look? So surprisingly, you have to look beyond this relevance boundary. You have to look outside of this relevance boundary. right? So because those are data that you thought were irrelevant before, right? So the interesting thing is that, like, if you look beyond your boundary, right, this relevance boundary, it's costly, right? And sometimes it could be wasteful, and you may not find anything, right? Because there's no guarantee you're going to find something outside. But if you do find something, it will be insightful, okay? Because it's something that you didn't know before, right? Because you thought these stuff out here are irrelevant. But if you do find something that turn out to be useful, turn out to be relevant, then it's something that you didn't know before. So by definition, they're insights that you didn't know, okay? So you have to look beyond that. So as very often when I talk to data science practitioners, for example, a manager data scientists, this is a trade-off they have to often make, right? So when do you tell data scientists to go and explore? And how much do you tell them to explore? And when do you tell them to stop, right? So this is actually comes with experience, right? So you can't look too far also, right? Because if you look too far, say like way out here, say like the phase of the moon or something like that, right? That somehow correlates with people's default rate, right? It may be, but good luck establishing causality there. Okay? You're not going to be able to find the causal link between the two, okay? So that's why, there's I would say, a fuzzy boundary between, where data scientists should look, right? A good data scientist, I would say a good one, should definitely look beyond what they think are relevant, okay? So think back at the case of Zest Finance. Who would have thought of, people's propensity to properly capitalize have anything to do with default rate, right? Like, who would have thought of that? Right? But the data science manager who managed those teams did not say that, oh, don't look at that, right? They say, go ahead, look at it, right? And guess what? And once they find that correlation, they actually test it, it is helpful, and that's insightful. And that's what gives them the edge in the market, okay? Because it's something they didn't know before, right? But guess what? After they made a PR out of that, very soon afterwards, everybody filled out their application with proper capitalization, and that term is no longer helpful anymore, okay? So they actually kept a lot of these things secret, but they discover hundreds of these unexpected features that are, I would say, correlated to people's default rate and actually helpful. But they actually use one to make I would say, a PR story for themselves, to illustrate the point, right? So they can't use that anymore because everybody knows about it, right? But then there's lots of other ones that they could use, right? They don't have to make public, right? So yeah, like I said, you may not find anything, but when you actually do, it will be insightful because it's something that you didn't know before, okay? So now, do business really want big data, right? Every business that I talked to today said, I'm drowning in data. I have a sea of big data, right? And we have lots of technology that deals with big data, but what we really want is the information and the insights, okay? So business, there's actually lots of technology down here. Business actually want the stuff up here, okay? And this is sometimes I call this the big data gap. There's actually lots of big data technology to help you manage, store, retrieve, and process big data, but there's not a lot of them actually turn them into business insights. So today, what do you do to turn this data into insights? Right? This is $1 million question, right? How do you turn those data into insights? All right? So turns out today, data scientists is the only way that business know how to turn their data into insights. And that's why data scientist is dubbed as the sexiest job in the 21st century, right? 21st century, yeah. So actually, if you actually look in this issue of Harvard Business Review, you found that quote, okay? I didn't say that. Harvard Business Review said that, okay? In fact, ever since I was in school, I would never imagine that anything I do in my life would be considered sexy. So, but, Harvard Business Review says so it must be true. So I'm sexy, so. All right. So I have to say that humor is actually not my strength. But I'm glad you guys are laughing. So all right. So now that you know, data scientists, right, or data science is essentially this bridge between data and insights. So what is data science anyway, right? So really is the practice of using data to solve business problem, right? To solve business problem, right? Anything that uses data to solve business problem can be considered as data science. Okay, So what does that involve? So typically, I look at that as 3 different layers of, and essentially that gives you an insight into the life cycle of data, right? How data is being used. Right? So we all are probably very familiar with what we call the decision science layer. The decision science layer are the one that actually typically interface with the business decision maker, right? So these are, dashboards, reports, or, that you can drill down and see reports of charts and everything to tell this decision maker how to inform the decision maker how to make a better decision. Right? So that's the decision science layer, right? But what people often overlook is that underneath this decision science layer, there's an algorithm layer, and underneath this algorithm layer, there's actually infrastructure layer. Okay? So let's start with this infrastructure layer. This infrastructure layer, it can be owned, right? You can actually own them, right? If you have a private cloud or something. So these infrastructure basically handles everything from the creation of the data, to capturing the data, to pre-processing it, to storing it, to retrieval of that data. Okay? So these are, the handled by the infrastructure. So when you actually, sometimes you don't have to own this infrastructure. Sometimes you can actually pay for it, right? For example, if you say you pay like Twitter for their entire fire hose, right? You basically are paying for this infrastructure, right? And the interface between the infrastructure and the algorithm layer is a query, right? The query that tells the infrastructure what data do you want, okay? Basically, you could just tell Twitter with their fire, if you have subscribed to their fire hose, and say, I want all the tweets, from May 20th to 23rd, and that has mentioned hashtag, outperform 2023, right? And they are geolocated in this Denver area, right? I could ask them for all the tweets that have meet those criteria, right? And they'll give it to you, right? Is whatever it is, give it to you. So the big important thing to notice with data is that sometimes the important thing about data is having access to it, right? Having access to it anytime, anywhere you want, that's the key. It's not, no one actually needs to actually keep a copy of those data, right? I'm sure all of you, no one actually here keep a copy of their entire internet on their home, right? But having access to it is good enough, right? Because that's how you derive value from it, right? So now, once you actually tell them what data you want, right, you go feed them into this algorithm. So there's actually 3 main types of algorithm here: descriptive algorithm, predictive algorithm, and prescriptive algorithm. All right? So descriptive algorithm, their job is simply to summarize data that already exists. Predictive algorithm, the goal is to estimate some data that they don't have. Okay? And then prescriptive algorithm is result of some optimization. Okay, so we'll look into each one of these in more detail. But after you actually do that, you have some results of these algorithms. Right? You basically feed them into this dashboard, and that's what informs the decision maker how to make a better decision. Okay, so let's take a look at these 3 classes. Any questions so far? No question, right? It's easy, right? Right? I told you there's no need for any statistics background for this session. So if it's too hard, you have to tell me, okay? You have to tell me, all right? So the first class, descriptive, right? So most of business analytics are descriptive. Approximately 75% are descriptive, right? So, and this number is actually, in the flux, So this descriptive is actually, they're not getting any less, but more and more people are doing predictive. So as a percentage, it looks like the descriptive is actually shrinking, but it's actually not. It's actually, the pie actually gets a lot bigger. So predictive is actually about 20%, and the rest of it is actually prescriptive. Okay, so descriptive analytics, like I said before, the goal is to simply summarize data that already exists, data that you already have. Okay, to tell you what's going on, right? So you've seen this all the time, right? So basically, when I joined the industry, I was kind of puzzled by this word analytics, right? Basically, people are telling me that analytics is what in the industry people do to inform them about decision. And after I done a little bit of due diligence on this topic, I say, really, analytics is just counting plus pretty reports, okay? And maybe you do a little bit of grade school arithmetic and some summations and averages and percentages, right? And maybe you do a little bit of Booleans and joins, and that's it, okay? So that's about it, right? So something very, very simple. And some people may say that, well, I don't know, people, like Google or Omniture, so they say, oh, we provide you with advanced analytics, right? Really, they're just counting plus pretty report plus some kind of filter, okay? So you say, oh, your traffics are coming from Europe, so you just filter it from Europe, right? So these are come from Asia, these come from this country, this come from that country. It's just, analytic with a filter on top of it. That's it, right? So something very, very simple. And underneath each one of those, it's just counting. You're just counting how much traffic you have, just tallying them up, right? There's actually no sophistication whatsoever, except I would say things that you could do with grade school math. So, all right, so not very interesting here, right? So obviously, all you need to do descriptive analytics is data. There's no shortage of data today, so anybody could do this descriptive analytics, right? And since this is an algorithm layer, so what is the algorithm? The algorithm is basically a few lines of SQL, right? Or if you may have a really complex SQL that lasts for a few pages, but it's just SQL, okay? So now, what about these fancy infographics? People often say, wow, all this like fancy visualization. What are those things? No, so those are just data, okay? There's actually no data science in them whatsoever, okay? It's just a presentation of the data. Okay, so I'm sure all of you have seen enough examples of descriptive analytics that I don't need to go into too much detail. But I do want to talk about this predictive analytics, okay? Because predictive analytics, a lot of people misunderstood what they do. Okay, when I talk about predictive analytics, what comes to mind right away? Come on. Forecasting, right? Okay, predicting the future, right? That's what comes to mind for everyone when we talk about predictive analytics. But in fact, that is just one use case, right? It is the most common use case, but it is just one use case of predictive analytics, right? The use case is called temporal predictive analytics. You're trying to predict in the time domain. That's why it's called temporal, okay? Temporal predictive analytics. So what do you do there? You basically have historical data, right? You build, this is the present time, you build a model, and then you feed these historical data into the model, and then out pops some kind of future data, right? That's what forecasting does. But keep in mind, there's actually a misnomer here, right? What? It is a snapshot, but this word here, future data, is actually a misnomer because there is no future data. You know that? There is no future data. It's actually a future forecast, a future prediction, right? Because you can't actually go and measure future data and come back and report it, right? You can't do that, right? That just violates physics, right? So just to illustrate that with an example here, right? Say today's kind of weather could be 62 degrees, right? And that is a number that you could go out and measure. You have to go outside with a thermometer or whatever instrument to measure that weather condition. This is a forecast. It's a 58°41, right? So this is actually not something that you actually measure, okay? This is actually a result of some kind of computation. It's output of some model, some kind of algorithm, okay? So, these, I would say, these predicted data, they're not real data, but very often they are actually treated the same as these ones, okay? They're not the same, okay? This one actually has a lot more uncertainty in them than this guy, okay? So these are, so just keep that in mind, okay? When next time you see it, you have to say, when people always say, like, we're predicting the future, data, so these data is about the future, you're not actually measuring it. It actually, there's a lot of assumption that go into your model, in your algorithm, whatever, right? And that's the output of those algorithms, those models, right? So it could be very, very wrong, okay? So predicted data, that's output of a model or algorithm, right? Should not be trusted 100%, never, right? You should trust them, you could trust them with high fidelity of confidence, 80%, 90%, but you should never trust them 100%, okay? That actually applies to generative AI today as well. Okay? All the stuff that's generated from generative AI, they are, again, outputs of some kind of model, right? So don't trust it with 100%. You need to do diligence, okay? Okay, so as I said before, temporal predictive analytics is just one use case. There's actually a more general predictive analytics that's actually not limited to the time domain. So what are you doing there? So this general predictive analytics, what they're trying to do is basically they're trying to use data that you have, right? You still build a model, right? It's the data that you have to estimate data that you don't have, to make an estimate of it, okay? That's why predictive analytics is all about estimation. It's all about estimation, okay? So as you can see right now that this temporal predictive analytics is just a special case of this general predictive analytics, right? The data that you have is historical data, right? And the data that you don't have that you want to make an estimate of is future data, right? And since you can never have future data, you can only estimate it from history, right? So it's just one, I would say, special use cases, right, of this. So to make that kind of a little more tangible, let's take a look back at the two examples that we looked at earlier, right? So with Target and Zest Finance. So Target, what are the data that they have? We'll talk about this. It's transaction data, right? So what they're trying to do is they're trying to build a pregnancy classifier, and the data that they have is purchase history, right? Quantity, yeah? Yes, that's in there too, right? That's who bought what, right, on all that stuff, right? So those are information that's in there, right? So you have that, right? But basically, transaction data is all they have, right? So basically, you feed this transaction data into this pregnancy classifier, it gives you a probability, whether this woman's likely to be pregnant or not. Okay? So that's, had nothing to do with time, right? You can actually take historical data, 5 years ago, and feed them in there to see who actually did get pregnant, right? So nothing about temporal here. It's not actually predicting the future. You could use it to predict future, but it's not predicting in the time domain, right? So same thing as Zest Finance. So Zest Finance, what are they trying to do? They're basically trying to do this a default predictor, right? You have online application as the data that they have, right? They have lots of those, and then they feed them into this model, and it outputs a probability of default from 0 to 100%. Okay? So what are some of the other examples that you might know? So I actually work in my previous role, I work in a social media company. So we actually produce something called the influence algorithm, right? So social media data are essentially the data that we have, right? So we can basically scrape that or buy that from Twitter or Facebook, whatever, right? So we could get things like who retweeted whose tweet, who followed who's friends with who, all this social media interactivity. Any kind of thing that you could do, who share a photo with who liked whose photo, all that stuff, right? All those are social media interactivity, right? You basically take all that activity, feed them into an algorithm, and then it basically tells you a score of how influenced you are, how influential you are. Okay? So that's one example. So in fact, sentiment analysis is also another example of predictive analytics. Okay? Because what are the data that you have in sentiment analysis? It's just text, right? Any text. It could be a tweet, could be an email, could be an article, could be a blog, could be any text, right? And then you feed them into the sentiment classifier, it will tell you whether you have positive, neutral, or negative sentiment. Anybody here know about sentiment analysis? Yes, it is. Yep. I mean, traditionally, it's actually used a lot in political polling, okay, to see how the public feel about particular candidate. But today, every marketers actually are using this sentiment analysis to see what their customers and prospects, their sentiment to the brand, to the product, or even to a marketing campaign. Okay. So they can see people's sentiment, right? So what are some other examples? So keep in mind, there's actually nothing temporal about this, right? You can actually, for example, with sentiment analysis, you could put like, say, Shakespeare's Hamlet in here, right? And see how Hamlet feels about life. In fact, so if you know what the answer is going to be, right? Hamlet's probably going to be pretty negative about life, right? So there's nothing temporal about this, okay? You could put historical stuff in there as well, okay? So this is another example. So I was visiting a Microsoft office, okay? So they basically have this camera feed that takes pictures or videos of people coming in, and they actually tag them with their age, gender, and whether they're happy, angry, or this emotion that they have, okay? Guess what? They got my age wrong, okay? So I'm more than double that age. So remember what I said about don't trust outputs of a model or algorithm 100%? This is a very good example of that, right? So it could be very wrong, okay? So, But keep in mind, this is an illustrative example because the data that they have is basically an image of a face, right? They could get that from a video camera or whatever, right? And they actually built 3 different models, right? They built like one, the age predictor that actually predicted age, but it's not a very good predictor, right? Kind of wrong completely, right? So you also get one, a gender classifier. There you got it right, so there. And they also have these emotional kind of classifier as well, right? Classify you into one of these 7 emotional state that you might have, okay? So again, these are the data that they have to make an estimate of data that they may find interesting and that they don't want to have but don't have, right? So that's what predictive analytics is all about, using data that you have to make an estimate of data that you don't have. Forecasting is just one specific example of that, okay? So remember I said forecasting is actually the most common use case. It is the most common use case, but if you actually add up all the other use cases of predictive analytics, that's actually much bigger than forecasting. Okay, so if you look at this one, all of these are predictive analytics. Right? Like even the sentiment analysis is predictive analytics. All that is actually, in total, is actually much, much bigger than forecasting. Okay, even though forecasting alone is the biggest, most common one. Okay, so in fact, Microsoft have this app, you can actually download, and actually they used to have it on the website as well. How old do I look? .com, something like that, and then you can actually go and upload your photo and see how old this algorithm think you look. Again, nothing about the future, right? You could actually, I don't know, put your grandma's photo in there and see how old was grandma when grandma took that photo, right? Nothing about future here, right? So these are predictive analytics, but not temporal predictive analytics, okay? All right, so let's take a look at the last class, prescriptive analytics. So as with, I would say, predictive analytics, right? There's, the simplest example of a predictive analytic is a trend line, right? That's in the temporal forecasting, temporal predictive analytics, right? And as I said before, there's general predictive analytics that's actually not limited to the temporal domain, right? So you've seen some examples of that, right? Several examples with images and how age predictor and all that stuff, right? So very similar, right? Prescriptive analytic, the simplest example is for example, a GPS navigation system. Okay? Because, why is it called prescriptive analytics? It's actually prescribing you things to do. That's why it's called prescriptive analytics. Okay? So how is this GPS navigation system prescribing you things? Basically, you tell me where you want to go, then I will prescribe you a sequence of action to get there, right? Turn left here, turn right here, go for 1 mile, make a left again, right? So these are sequence of instruction on how to get there. I'm prescribing you things to do to get to your destination. That's what prescriptive analytics do, right? Okay, so just like I would say predictive analytics, right? That's actually, I would say, not limited to, I would say, temporal domain. Prescriptive analytics are not limited to the geospatial domain either. Right? You can have, the general prescriptive analytics is, could be, it could be prescribing business strategy. For example, your CEO may tell you that I want to increase sales by 5% by the end of the year. What is that? That's this. That's your destination, okay? And if you have the data, right, you have the proper data for this prescriptive analytic system, they would be able to prescribe you sequence actions, right, of how to get there. Maybe you have to price better, you have to hire more marketing, or do whatever. If you have the data to feed them in there, it will be able to prescribe you what to do to get to that 5% increase in sales, which is your destination, okay? So now keep in mind, the verb that I associate with prescriptive analytic is optimize. Why do you think that's the case? Any guess? Right? Keep in mind, look at this. From here to here, there's actually lots and lots of different routes to get from here to here. Right? You can actually go around the river this way, come back. You kind of come around this way. You can even go around the globe and come back the other way. Right? There's virtually infinite number of routes to get from A to B. Why do you think it prescribed this particular one? Yeah, it's the most efficient, right? So let me ask you, what do early GPS optimize for? The oldest kind of GPS, what do they optimize for? Distance, right? They give you the route that's the shortest distance. You key in the destination, right? I will give you the shortest distance route to get there. Early GPS do that. Today, GPS is smarter, right? What are they actually optimizing today? Time, right? Travel time, right? So basically, now, travel time actually depends on a lot of things now, right? Because travel time could depend on the traffic condition, depends on weather, right? So maybe you have some region that's flooded, right? That's the roads closed, right? So it depends on a lot of things. So if you actually key in the destination, right? It may not give you the same thing every single time because now the traffic condition may be different, the weather may be different, right? So now, but keep in mind, there's one thing in common is that all of them actually do optimize for something. Right? Early GPS, optimized for distance, shortest distance. Current GPS, optimized for shortest travel time, right? I think even some of the newer GPS, right, they even optimize for, carbon footprints or something like that, right? Maybe you could take some carbon less, I would say, routes that are have less impact on carbon footprint, right? So they do that, right? They're optimizing for something, right? So let's take a look at some other examples that you know and are actually very familiar with. So today, you probably have Netflix at home, right? So these recommender systems here, they're recommending you content to watch, is essentially prescriptive analytics, right? So just like the case with the geospatial domain, there's virtually an infinite number of routes to get from A to B. There's also virtually infinite number of movies or music or whatever that you could watch and listen to, right? Why do you think they prescribe you this particular set? It's optimizing for something, right? So what is optimizing? Yeah, engagement, right? Basically, it's optimizing the similarity of your preference to the content, right? If you like sci-fi, it's going to give you more sci-fi. If you like, drama, it's going to like more drama, right? So it's optimizing that, right? So basically, there it's optimizing the similarity to user's preference, optimizing the content to the user's preference, right? How about this? Again, just like the geospatial domain, there's virtually infinite number of web pages out there for you to surf. When you actually go Google or search for whatever content that you want, it gives you 10. Right? It's prescribing you those 10. Go look at those 10. It's prescribing those things for you to take action on, right? Why do you think it prescribes you those 10? What are they optimizing? Relevance to your query, right? Okay? So to understand prescriptive analytics, really you just need to ask a very simple question. What are they actually optimizing underneath? Okay? And to understand predictive analytics, you just have to ask the question of what data do they have to make an estimate of what data that they don't have, okay? So with that, you basically get a Bachelor of Data Science, okay? So congratulations. Easy, right? Nothing confusing, right? Yes? Good, okay, so let me go on. Okay, so let me take a drink of water. Any questions so far? No questions, so I'm not sure if you're confused or lost or bored. What? Okay. Yes? Mm-hmm. Yeah, you see that here. Just give me a sec, okay? Yeah, you will see that. You're ahead of everybody, so thank you for the question, okay? So what do data scientists do, right? So now that you know that data scientists, data scientist is the sexiest job in the 21st century, so what do they actually do, right? So now if you actually ask a very simple question, right? The best way to understand what data scientists do is to ask what is the input and what's the output of a data scientist, right? So what do you think the input of a data scientist is? Data, right? Data scientists take data as input, right? What do they produce? Right. Okay, so let me tell you, all those are right, okay? There's actually two main classes of output from a data scientist. One is some kind of model, some kind of algorithm, okay? And the other one is some kind of report, some kind of data visualization, some kind of dashboard, okay? So when you actually go from data to this visualization, some kind of report, some kind of dashboard, this is called data mining. This function exists, okay? Especially in the financial industry, insurance industry, they exist for a long time. Now, when you actually go from data to some kind of algorithm, some kind of model, that's called machine learning, okay? So whatever people tell you about machine learning, right, forget about them. Okay? The simplest way for you to understand what machine learning is simply the process of turning data into some kind of model. That's it. However they want to do it, you know, it's up to their choice, right? It's up to their expertise, right? So machine learning is simply the process of turning data into some kind of model, okay? So what does that involve? Step one, okay, is really getting the raw data. You have to get data first, right? So now, you know, getting the data, you know, if you actually look at, remember, you know, this is the sexiest job of the 21st century, right? So now, this, if you actually look at the job description of a data scientist, somehow they don't look too sexy, right? If you actually look at them, they look like these normalization of type range, exception handling, right? You have to handle like messy data. You have to, you know, deal with incomplete data, duplicating data, and all that stuff, right? Tagging, metadata tagging, all that stuff. So all these are, I would say, very mundane, repetitive, rather kind of boring job, right? So they're not so sexy, right? After all, right? In fact, you know, it looks kind of like this, okay? And in fact, about 50% of a data scientist's job today is just data generating, just cleaning up data, okay? To your point, right? Cleaning up to the point that where you could be useful enough for you to visualize, for you to actually put them into an algorithm, okay? So this number is actually trending down. So earlier in the days of, I don't know, how many people here actually do manage data scientists? Do you manage data scientists here? Anyone manage data scientists? Nobody actually manages? Okay, you do, okay. So how much time do you think they actually, huh? Yeah, so, but what I want to get to is that like this percentage, right? So this percentage used to be higher. In fact, if you actually talk to companies, right, a lot of people actually claim a much higher number. Some people say like my data scientists spend like 80% of the time, you know, data janitor and cleaning data, right? And some people say even like 90%. So in my experience, that's a little bit high. Okay, that's a little bit too high for today's standard, I would say, okay? And I would say that those companies, they probably don't have a good enough infrastructure layer, okay? Remember those 3 layers that I talk about in data science? If they have a strong, robust, I would say, infrastructure layer, their data scientists should not spend that much time on process, you know, just cleaning data, okay? So they should, you know, I think 50% is about right, you know, for today. I mean, and as the infrastructure layer of technology become better and better and more accessible to the company, this number will continue to go down. But for today, it's about right, okay? On average, you could be very advanced and do better than this, okay? So now, getting the raw data. So what do you mean by raw data, right? Raw data is really just, it could be any kind of data. It could be text, could be image, could be numbers, right? The key thing is that they're measured directly, okay? That's raw data. So your weather forecasts are not raw data, okay? They're outputs of a model, right? You should not trust them, right? All right, so those are not raw data, right? So raw data is things that you directly measure, right? You could directly go on and measure it, right? So you have to very often validate that it is actually truly measured, right? But raw data is actually very hard to work with, right? So for example, this text right here, you could read them, but what does it look like in the computer? In the computer, it actually looks like this. Anybody know what these are? These are the ASCII code of these characters on the screen, okay? Inside the computer, this is what it looks like, okay? All right? So they're very hard to work with, right? In fact, so let me just give you another example, right? So this is actually a picture of something. So what is it? What is a picture of this of? Any guess? It's very hard, right? Let me even tell you a little bit further, right? 1 represents white color, and 0 represents black. So can you still tell what's this picture of? It's not easy, right? This is simply the letter A. That's it, right? It's very, very hard to see this from this array of number, isn't it, right? So now, the question that a lot of people are often asked, like, I mean, can we build some kind of computer vision algorithm to tell me, say, a picture of a bird from a plane, right? So this is definitely possible, right? So we're going to actually go into this a little bit of the process of how. How do you actually do that? Okay, the question is how, right? So but before I go into that, I want you to think about how difficult this problem is. Basically, what you want to do is you want to build some kind of algorithm, some kind of model, right? Some kind of function, right? Where when you actually put one picture in there, it will tell you that the output is 0 that represents a bird consistently. Anytime you have a bird, it's going to give you 0, okay? And if there's a picture of a plane, it will give you a 1 that represents a plane, right? Consistently. Anytime you have a picture of a plane, it will do that. Now, think about how difficult this problem is, because these images, they are just an array of number, right? You have to take a look at that array of number, right, and determine whether there's actually a bird or plane, or what should come out of it should be a 0 or 1, right? Think about how difficult this is. In fact, this is actually, these are color photos, these are color images, right? So these are actually 3 different arrays of numbers here, okay? Very, very difficult problem, right? So people often say that, well, this must be the information that tells me whether this is a picture of a plane or bird has to be, it had to be in the pixels, right? So in fact, if I actually take any random pixels, right, they will find that, they're about 50% of them the time they're part of a plane, and then 50% of the time they're part of a bird, right? So basically, it's a random guess. So it's not telling you whether it's a bird or plane, right, at all. Right? In fact, if you actually take like a couple or a pair of a pixel, right? Take any pair of pixel, right? The probability of it kind of being part of a bird is all over the place. The probability of being part of a plane is also all over the place, right? So what that means is that these pixels are not telling you whether these images contains a bird or plane, right? So how do we actually determine this? Obviously, we know this can be done. The question is how, right? So this is, we have to come to this concept of feature, okay? So turns out that pixels are really, really bad features, okay? They're bad features. So what is this feature, okay? So it turns out raw data is not only noisy, dirty, they're actually bad features, right? They're bad features. So let's try to understand what features are, okay? So features are basically, okay, I want to contrast that with raw data. Raw data, again, is data that you measure directly, right? So feature is basically information that you derive from the raw data, okay? So remember the difference between data and information, right? Information is what the data is able to tell you, okay? So think about that. It's what the data is able to tell you, right? So these are the information that you derive from these raw data, right? So let's take a look at the example of Zest Finance again. You're going to see this example a few times today, okay? So remember, the raw data is the data that you measure directly, right? It's the input from the user, right? It has, for example, the person's name, their age, their ID, info, the loan amount, income, spending, all that stuff that you fill in when you apply for a loan, okay? So that's the raw data. So now, raw data don't perform very well, right? We've seen that with the case of telling you whether an image contains a bird or not, right? In fact, if you actually try to use any of this information to predict people's kind of default rate, right, they actually don't do very well. For example, you could look at people's name and see how much they each name default. Like, guess what? Do you think people's name tell who's going to be default more or less? What do you think? Probably some people. I hear some people say yes. Why? Okay, so people. Okay, so let me caveat that. Okay, so if you actually normalize the default rate, right, then it's actually pretty much flat. Okay, I mean it's actually not able to tell you which name defaults more, right? But if you actually look at the number of people who default with a certain name, some names may actually default more, right? For example, Michael, my name, right? It's very, very common. Unfortunately, I blame my parents for that. Right? So if you actually look at all the people who default, Michael will probably have much more default because, but that doesn't mean that people's name are Michael are more likely to default. There's simply a reflection of the fact that there's more Michaels out there. Okay? All right, so we talk about feature, right? So now, if you use these raw data to help you determine whether someone's going to default or not, they don't work very well. okay? As I said before, right? So if you actually look at names, right? If you look at names like these, this axis represents like, all the names with A's, B's, C, all the way to Z's, right? All the higher. So these people are gonna default, with different kind of default probability, right? So, but if you actually normalize it for the amount of names out there, for how frequent those names occur out there, they're pretty much flat, okay? If you don't normalize it, the more common names, of course, like like Michael or David or someone who has a very common name, you're going to see a bit more of them defaulting, having that name. But that doesn't mean that people with those names are more likely to default, right? It's just a reflection of the fact that there's more of that name out there, okay? So if you actually normalize for those names, then it's very, very flat. So now let's take a look at what about loan amount. Do you think people who borrow a lot of money defaults more, or people who borrow little money defaults more? What do you think? A lot of money. It turns out that if actually if you normalize for how much, how frequent people borrow a different amount, they are again flat. Okay, they're again flat. All right. So it turns out that like a lot of people borrow little money, a few $1,000, $10,000 for their car, or for their house, or project, something like that. But very few people borrow a lot of money, right? So if you actually normalize for the the loan amount, the amount of loan amount out there, right? Then again they're flat. Okay. So now, what about income? Do you think poor people defaults more, or rich people defaults more? Rich people. Okay, turns out, again, if you normalize it for the amount of rich people out there and the amount of poor people out there, they are very flat again, okay? So interestingly, if you actually look at age is actually very interesting. So, young people, so you say you start with 18 or something like that, right? So if you get to really, really old age, they default slightly more. Why do you think that's the case? Yeah, people die, right? So, right, at old age, people die. So this is a reflection of the fact that at old age, people actually pass away, right? It doesn't mean that elderly people don't have the ability to pay back, right? So this is again, so this is actually reflected in the data, right? So it turns out that if you actually look at any of these raw data, right, if you actually normalize it a little bit, right, it's actually not a very good indicator of whether people are going to default or not. Okay, they're not very good, right? So how do we get to a better kind of indication of people's default probability, right? We compute something, right? So we compute something called the loan-to-income ratio, right? And we compute something called the debt-to-income ratio. So can you see why that's actually much more indicative of people's kind of default rate, right? It's okay if you're poor, but if you're not borrowing a lot, it's fine, right? If you actually, if you have a lot of debt, right, and you're rich, that's perfectly fine, right? It's no problem. If you have a lot of debt and your income is low, that's a problem, right? Okay? So these are, I would say, very simple features, right? It just takes I would say, take the raw data and you just take a ratio and you compute it, right? So to extract the information from this raw data, you don't have to do a lot of work. You have to do some very, very simple amount of work, okay? Right? So that's, so these are the features, right? So how about this one? Now, do you think this? Certainly this information is in there, right? The loan-to-income ratio is certainly in the raw data, right? It's not explicit, right? But the information is in there. That's why you could calculate it. Okay? Keep that in mind. All right. Looks like we recover some brave souls now. So people are kind of trickling back in. Okay. So now, in fact, if you actually look at any one of these features, right, they are actually much more discriminant. Okay, they are much more discriminant in the sense that, they actually tell you that. So how about this information, right? This information, the frequency of late payment or early payment or the income spent volatility, right? So these information, do you think this information is actually in the raw data? They're certainly in there, right? Because you can actually take that, their payment habit, right, and actually, do some kind of average, over every month that they actually pay, right? See how frequently do they pay early or pay late, right? So you could calculate that, but you have to do a little more. Keep in mind, you have to do a little bit more work to extract that information, right? So this information is in there implicitly, right? and then you could extract it by doing some calculation, right? But still very simple calculation, right? Very, very easy, right? So, but then the point is that like you actually get to some kind of variable that are much more indicative of people's default rate. Okay, so in fact, if I take any feature, they are telling you, who's gonna, basically it's telling you that these people are much less likely to default. These people here and here are much more likely to default. Okay, it's much more discriminant. When you have a flat probability, right, they're naturally not telling you anything at all. Okay, so now how about this one? Do you think the information of whether people, properly capitalize in their application, do you think this information is actually in the raw data? Come on. Yeah, it's in there, right? But you have to do a lot of work to get the information out, right? You have to kind of look through the application, check every pronoun, every noun, to see if they're properly capitalized. You have to parse the text and everything, right, to make sure. So you have to, you can, but the information is certainly there. But keep in mind, nowhere in the application did they ever ask you, did you fill out the entire application with proper capitalization, right? Nowhere did they ever ask you that. So that information is never explicit. It's never asked explicit, but the information is implicitly available. You have to do some processing, some kind of analysis to extract that information. Remember, these are information, right? This is data, this is information. Features are essentially information, right? They extract, right? So how about this? How about the number of times you save before submitting the application? Do you think that information is actually in the raw data? Come on. Yeah, because everything is probably timestamped, right? Everything is timestamped. Now, how about this average time between saving and opening the application again? Everything is timestamped. You could calculate that, right? Now, the question is, do you think that's relevant? Do you think that's actually useful in determining people's default rate? Right? So at the end of the day, right, it really doesn't matter if it's important or not. It matters at the test, right? So just like the case of proper capitalization, it really doesn't matter. You could hypothesize, maybe people who don't fill out the application with proper capitalization, maybe they are not as attentive to detail, so they may not have a job that requires, a detail-oriented job, right? So as a result, they have lower-paying job and therefore less likely to pay back the loan. You can hypothesize any way you want, but the ultimate test is at the test, right? When you actually use it to augment your traditional underwriting, does it help or not? If it helps, it helps, right? If it doesn't, it doesn't, right? So these things again, right? If you could hypothesize, you can say that way, say the average time between opening and saving the application is like a week, right? You can hypothesize, oh, maybe it's taking him so long to fill out the application, maybe he doesn't need a loan, right? You can hypothesize any way you want, but at the end of the day, you have to use it to test it to see if it actually does help you determine people's default rate, right? So let's do a few more of this, right? So how about the day and time of the week for filling out the application? So this one, people could hypothesize again, it's actually very, very important because if you actually fill out this application that took you 3 hours long and you fill that out in a work day during the work hour, maybe this person don't have a job, right? Right? You can hypothesize why this is important, but at the end of the day, right, it matters when you actually apply it to see if it actually helps you determine people's default rate, right? That's the ultimate test, right? So Zest Finance also, ask you to take a photo of your driver's license, your ID, to make sure that you are who you say you are, right? So they can actually use optical character recognition to extract information from this picture also. Right? For example, they could extract their hair color, their eye color, their height, and their weight. And again, do you think these features are useful in determining people's default rate? So most people would think not, right? Okay, but guess what? What they find is that, like they said, taller people, right? Height is big, and there's taller people default slightly less than people who are short, okay? So this one, just like the use of proper capitalization, they did not believe it at all, okay? And they actually gone and actually tested this and to see if it actually improved their prediction accuracy for their default rate. And guess what? In this case, it actually did not help, okay? So that's the test, right? So you could hypothesize all you want. You could say, oh, tall people may appear more confident, so they are probably better sales, right? So they probably make more money than the shorter guy, right? So maybe they are, have more ability to pay back the loan. You can hypothesize all you want, but the test says that, when you actually apply it to augment your traditional underwriting, it doesn't actually help you predict people's default rate any better. So it doesn't matter. Hypothesize all you want, right? So, okay. So how about like this one, okay? Do you think this information is in the raw data, right? So where did they actually fill the application? Do you think that information is in there? Yes, no? Through what? IP address, right? Right? But keep in mind, it actually takes a lot of work to get from an IP address to people's actual location, right? Do you know how to do that? It's not that easy, right? You have to, call some kind of geo-IP packages, right, to get that, right? So keep in mind, right, we started with very, very simple feature, right? This feature, just take a simple calculation, right? And you have more complex calculation, and you have to do more text processing, and even optical character recognition, right? These are more and more sophisticated information they have to get to extract out of this raw data. But think in terms of information. If these information are in there, right, then you can do something to get it out. It may be very hard to get it out, but you could do something to get it out. But if the information is not there, you can never extract it, right? Okay? So how about this, right? This is it sunny or rainy when you actually fill out the application? Right? So this one, again, so this information is actually not in the raw data per se, but it's actually derivable, right? You could get the geo-IP, you could get the time, right? And you can actually use that information to call a weather service to get the information whether there is raining or not, right? So whether that's actually useful or not, test it, right? Okay, so that's in fact what data scientists do, right? So basically, there is a process in data scientists' job. It's called feature engineering. Okay, so feature engineering is the extraction of implicit or externally derivable information from the raw data. Okay, so that feature engineering is a process of turning raw data into feature. Okay? Okay, and guess what? Why is this important? Because if once you have the right feature, the problem that you're trying to solve becomes a lot easier. Okay? A lot easier. So let's come back to this problem of determining whether a picture is a picture of a bird or a plane. Okay? What are some good pictures of a bird? What do birds have that planes don't have? They all have wings. What are you talking about? Right? What else? Beaks, right? They have beaks. They have and maybe they have feather. They have feet, right there. So these are, so basically this process, right, of turning raw data to feature, right, is feature engineering, right? So birds actually have beaks. They have eyes. They have, feet. They have feathers, right? These are things that planes don't have, right? What are some good features of a plane? Engines, right? Windows, right? You don't see birds with the windows on their side, right? So window, right? So these are perfectly good features for plane, right? So if you have those features, right? So keep in mind that you have to do some work to extract those features, right? So basically now, let's take a look at how we built this model. Once you have this feature, it's actually relatively easy to come up with a model that tells you whether you have a picture of plane or bird. Okay, so let's take a look at just one feature from bird, one feature from a plane, right? So basically, the probability we have this axis called the probability of seeing a beak and probability of seeing a stabilizer. So stabilizer is essentially the tail part of that plane that stabilizes the plane so it doesn't fishtail. Okay, so let's take a look at these images, right? So these images, if you actually look at these three images, you could definitely see the beak, right? If you actually zoom in, I know it's pretty hard, especially for people in the back, you could definitely see the beak there, right? So the probability of seeing a beak is very high, right? So to do that, you have to do some image kind of feature matching, right? Just run through the image. You have to do some work to get that out, but you could do it. It's actually not hard, right? This is so Now, this picture is actually interesting. This one right here, the bird is actually looking directly at you, okay? So it's actually pretty hard to see the beak. If I actually mask out all the rest of the bird, right? And basically, it's not quite sure. You can't really tell with confidence that it's a beak or not, right? So basically, the probability of seeing a beak is you're not quite sure. It's about 50% here, right? So now, but still, there's nothing that looks like a stabilizer for all these birds here, right? Okay, now, what about planes, right? So let's planes right here. So that one is a dead giveaway, right? So you can definitely see the stabilizer here. So high probability of staying a stabilizer, but nothing that looked like a beak here, right? Nothing that looked like a beak. So it's low probability of having a beak. So what about these two? This one and this one right here. So this one, you could definitely see the stabilizer, but if I cover the rest of the plane, it's just 3 lines. It's not, you can't really tell that it's a stabilizer or not, right? So this one, you can tell it's a stabilizer, right? So this one, slightly higher probability, right? So this one, there are some part of it that actually look kind of like a beak. This sharp wing right here maybe look like a bird with a really long beak. If I cover up, in fact, let me just do this. Okay, if I cover up, kind of the rest of the plane here, this little thing right here looks like somewhat like a beak, right? So it's slightly higher in probability of having a beak, right? But that Concorde jet there is very, very interesting because guess what? If I cover the rest of the plane, this nose of this Concorde jet actually do very much look like a beak, right? Right? Okay? But you also see the tail stabilizer here. So it has something that looks like a beak, but it also has a stabilizer, so it's high there, right? But now you can see how these features can actually divide this data into 2 classes. One is a bird, one is a plane. Right? You can actually create a model that tells you whether it's a plane or bird, right? And you can even use a very simple linear model, a line, right? Things that are kind of on your upper left are likely to be birds. Things that are on your lower right are likely to be planes. Okay? That's how you come up with a model. Okay? All right? So this model actually usually comes from some kind of objective function that you maximize. So we talk a little bit about that later. So now, remember I talk about what is machine learning again? It's the process of what? Turning data into a model, right? It actually has 2 steps. One is feature engineering, right? One is obviously the statistic. You have to do some statistics, do some math to turn it into a model, right? But it actually also involves feature engineering, right? Feature engineering is one of the things that nobody talks about it. In data science, is very common. We talk about this all the time. But outside of data science, nobody talks about it because it's very domain specific. What the good feature in one domain for one problem, it may not be applied to another problem, right? So these are very domain specific, right? So that's kind of what machine learning is, right? Machine learning actually involves feature engineering, getting your data and turning them into what we call informative feature, good features. If you have a good feature, it makes your problem a lot easier, okay? And then you have to do some math to turn that into a model, all right? Okay, so it turns out that data science is actually about 25% crafting of these features. You have to essentially come up with these features. These are essentially created, so yeah. So let me ask you guys, do you think I'm a dog person or a cat person? How many people say I'm a dog person? How many people say I'm a cat person? Surprise, surprise, okay? So interestingly, so how do you determine that? That's right, okay? So if you actually look back at this presentation, right, I used many pictures of dogs. Remember the Target dog, right? The Schnauzer, the Jack Russell with the big data, noisy, right? I never used a picture of a cat, right? So that information, right, how many photos of dogs I use, how many photos of cats I use, could be a feature to determine whether I'm a dog person or a cat person, okay? So these are essentially feature, right? Nowhere did it ask you that I'm a dog person or a cat person. It's not explicit, right? But you could tell by doing some work, doing some maybe sometimes very difficult analysis on the data, which we've seen so far, right? I mean, to extract how many photos of a dog that I use in the slide, or how many pictures of a cat I use in the slide, right? But that information is there. So you could actually take my slide and run it through some kind of algorithm and determine that, right? It may take you a little work, but it's doable. Make sense? Okay.
In the previous slide, you were showing that photo that was taken, determining your age and your recognizing. Now, if we relate that to the bird and aeroplane example, how does it work?
I didn't quite hear that. Can you give me a mic? Or, sorry. Why don't we put a mic in the middle? So can I have someone maybe help me get the mic to the audience so they could, because I can barely hear you.
So the question is related to the example you shared earlier.
Can you talk closer? Yeah.
The example you shared earlier, where by looking at your photo, the machine was recognizing the age and the gender. If we take that example and try to map it with this aeroplane and the bird example.
You mean this one?
No, the initial.
Early on when I visit Microsoft Office.
Yeah.
Yeah. Okay.
So how that works in a nutshell, right? Example, how they recognize the age and gender. Is there any?
Yeah. Again, features. Okay. So they actually derive features of people, that are 20 based on, maybe their hairline, the amount of wrinkle they have, So all that is basically features. Okay. They actually do it by, so you can actually, create a age, predictor by just looking at features on what you think are elderly feature or how much of it is actually present. Okay, they're not very sophisticated models. That's why they get my age completely wrong. Okay, so but it's a rudimentary model, right? So but it does, I would say, work better than random chance. Okay, if you actually put a picture in there, it will actually do a decent job. Right? For me, it's happened that it didn't, maybe I'm wearing a hat or something like that, right? So I didn't see all the white hair that I have. So I'm covering evidence of my age, right? So it's not able to determine that very well, right? So, okay? All right. Okay, so let's move on. Okay. All right, so now I'm a dog person, right? But surprisingly, because my wife is a cat person, so we actually have a cat, not a dog at home. Okay. So we talk about feature engineering, right? Feature engineering is just the process of turning your raw data into feature. And features are, I would say, variables, data attributes, right? That is much more informative and telling you, addressing your problem, okay? And they are typically implicit informations that are not very obvious. You cannot just look it up. You have to do some analysis to extract those information, all right? So now let's take a look about the second step, doing the math, okay? Remember, I said that you do not need to have math. I did not say that you don't need to do math, okay? You do need to do some math, but it won't be difficult, okay? So there's actually a lot of learning paradigms. These are called learning algorithms that actually turns your, the feature and the data that you have into a model, okay? So the most common one that people are very often heard of is supervised learning and unsupervised learning. Okay? But in fact, these are just two, I would say, very common ones that people heard. But there's actually a lot more. There's actually deep learning, there's reinforcement learning, adversarial learning, semi-supervised learning, active learning, self-supervised learning. This actually is the kind of the cutting edge around. These are the methods that's actually used to train ChatGPT, okay, which you'll hear about tomorrow in the keynote. So online learning, one-shot learning, few-shot learning. So these are, even transfer learning, transductive learning, ensemble. So there's actually lots and lots of these learning algorithms that turns your data and feature into a model, right? So in fact, this is there in, there is no Nobel Prize for computer science. But in computer science, we have something called the Turing Award, the Alan Turing Award, in honor of the father of modern computing, Alan Turing, right? So Alan Turing Award was awarded to 3 recipients in 2018. And these are the 3 recipients, Yann LeCun, Geoffrey Hinton, and Yoshua Bengio, okay? So, so actually, very interesting. So at the beginning of this year, I was at a conference in Morocco with Yann LeCun, and we were talking about how we could apply some of these deep learning. So the interesting thing to know is that the 2018 Turing Award was awarded for these 3 recipients for inventing the deep neural network, okay? So all the things that you see today with ChatGPT, or all this image generator that involve deep neural, even our product, okay? Our Gen 4 price optimization has deep neural network in it, right? It's because of them. Okay, so, all right? Okay, so Jan LeCun, okay, so he basically had this interesting analogy. He basically says that, so today, if you actually look at the information per, I would say, sample, okay? If you train a model, you need some data, right? So how much information does each data point hold, right? That's what we call the information content, right? So basically, he said, reinforcement learning is like the cherry on top of the cake, okay? So basically, it predicts a scalar, or a single variable, right? That's actually, it only gives you a few bits every sample, right? So in fact, this actually is not very good for very high dimensional problem in the realistic world, right? But so reinforcement learning has worked very, very well in, I would say, a simulated world, in like playing games and stuff like that. But they don't work very well in the real world, like for example, driving, self-driving application. They don't work very well. But they do work in real world problems that are low dimension. So in our example, in our world where we do like price exploration, right? So that's a scalar. That's actually a much lower dimensional problem, right? So that actually works fine. Okay, but if you're actually trying to do very large problem, they don't work very well, okay? So then you have supervised learning. Supervised learning, right, all the different kind of learning out there, there are algorithms that I showed before, right? Supervised learning is actually, it actually makes use of the data fairly efficiently, much more efficiently than reinforcement learning, right? To make reinforcement learning work, you need like, trillions of trial, right, of trial and error, right? And in a game, a chess game or Go game, right, you could simulate that, trillion game, no problem, right? But in the real world, you're not going to get a trillion sample, right? So in the real world, you get like maybe 10,000, 100,000 data sample, and that's why supervised learning is actually kind of the icing on the top of the cake, right? So this notion of self-supervised learning is the method that they use to train ChatGPT and large generative AI today. This is kind of the cutting edge research now. So today, this is actually not, I would say, very efficient yet, okay? So basically, even though this is basically the rest of the cake, right? It's actually not production ready. A lot of these things actually require highly specialized hardware and highly specialized to make this work. So basically today, the industry is pretty much stuck with supervised learning, right? So this, they could work in some cases in low dimensional problem. And so here they are mostly industries actually using this. Self-supervised learning is actually hard to make this work for a lot of the use cases, right? So now let's take a look at how supervised learning algorithm actually learn, okay? So here is where we actually need to do a little bit of math, okay? So, but bear with me, okay? It will not be difficult, right? So there is some system that we're trying to model, right? So this system can be a human, can be a market, can be anything, right? So we have a system. And then there's also the learning algorithm, right? So we call the system, the algorithm, the learning algorithm, we're gonna call the algorithm, right? So basically, the system, right, is usually will have an input and an output, okay? The input, so these are the input to the system and output of the system. All right, so these examples of this could be, for example, the plane, right? The input could be a picture of a plane, and the output would be, a label, say that is a plane. And the picture could be a bird, and the output the label of a bird, right? So these could be the input to the system. This could be a human labeling this output, calling it a bird or a plane, right? Or, so this would be a classification problem. If you actually train this AI to mimic this human, you will classify them into two classes, the plane class and the bird class. Okay? Now, it could be other things. For example, it could be a chest X-ray, right? So this system could be a doctor, okay? The doctor could actually look at your chest X-ray and say that, okay, you have cancer, you look okay, and you probably should be dead a few months ago. so that's, so that's the doctor's kind of assessment, right? So the input will be chest X-ray, the output will be, his assessment of your condition, okay? So these are, essentially, again, a classification problem, right? You put in the image, and it's actually telling you whether you have cancer or not, right? But it could be time series as well. For example, you can actually, have time series that look like this, and then you have maybe some analyst telling, this system can be an analyst, right? Basically, making the recommendation whether to hold or to buy or to sell, right? So these could be the FANG stock, right? And then, these are maybe their recommendation. So this would be, again, a classification, but you wouldn't be a two-class classification. It would be called what we call a multi-class classification. You classify them into a buy, a hold, and a sell, right? 3 different classes, 3 different possible output, right? On the other hand, there could be something much more complex like what we do, right? We are trying to look at all the attributes of a trip, right? And then basically produce an airfare, a price for the fare. And so that would be what we call a regression problem, because now the price can be any continuous variable, right? Can be $100 or $150, right? So it could be any number, right? So you can't use a classification anymore, right? Okay, so these are just examples, right? So basically, when you so you've seen plenty of examples of input data to the system and output data to the system, right? Now, if you take the input to the system and the output of the system, right? Both of these are input to the learning algorithm, okay? So that's a little confusing here, right? The input of the system and output of the system are both input to the learning algorithm, okay? So you basically feed these into the learning algorithm. Your algorithm is simply trying to map the input to the output to trying to mimic what this human is actually doing, what this system is actually doing. So that's supervised learning, okay? That's supervised learning, right? That's basically, you could think of supervised learning as just brute force learning by seeing many examples. I'm going to show you one example of, say a bird, a picture of a bird, and then, that's a bird, and then actually you are basically essentially trying to replicate what the humans do to reproduce those data, right? But keep in mind that you had to be able to generalize. You cannot just memorize every photo of a bird or plane. If I give you a new picture of a bird or plane, right, you have to be able to tell me reliably whether they're a bird or plane. If you're simply remembering it, that's not going to cut it, right? Because if I give you a picture that you've never seen before, you would do horrible. But having the feature that tells you what is a bird and what's a plane really help, right? Because if it's a picture of a bird, it's going to have those features again, right? Maybe not in different orientation, right, and different things like that, but enough features of birds being present would tell you that, would signal that strong presence of that bird, or if that is a bird rather than a plane. Okay, make sense? All right, okay. So how machine actually learn from data? So this is the key thing, right? So we have input data and output data, right? So the input data, typically we actually going to label them as X. We're going to call them X, right? So these could be, basically any input data can be, I would say, what we call vectorized. Turn them into just an array of numbers, right? And the output is basically some kind of a label, right? We call them like, for example, a bird, right, or something like that. That would be 0 or 1, right? Okay, so most input data can be represented as an n-dimensional vector space, right? So what that means is that even if you have a picture or image like this, right, I could simply, turn these pixels, stack them on top of another, right? Basically turn them into a big, long array of number, right? So that's why this is called a vector space, right? So you have an n pixel, that will be an n-dimensional vector space, right? So that is just basically just nothing more than an array of number. As I said before, right? An image is nothing more than an array of number to a computer, okay? All right? All right? So once you have that, when you actually look at this, right, this actually, if you actually look at it in terms of a vector space, it's really just a point in the n-dimensional space. Just one point, one dot, right? If you have a 3-component, if this was only 3-component, you'll be an X, Y, Z. But then, because there's n component, right? I can't show n component in this picture, right? So it's just one point, one dot in the abstract space, okay? Okay, so that's what the input data look like, right? So if you actually have a whole bunch of data, whole bunch of data points, right? They're going to be a whole bunch of points scattered in this n-dimensional space, right? Now, y is just one number, right? So again, so that one you can actually put this input map them into we're going to represent them in the axis, but they really is an n-dimensional space, and represent the output as a y-axis here. right? If you do that, basically what you're trying to do is you are trying to simply find a function that maps x into y. That's all. That's all you're trying to do. Okay? Right? It's basically curve fitting, right? You're not fitting a two-dimensional curve like this. This is actually a very high-dimensional hypersurface that you're trying to fit. Okay? So basically, a lot of machine learning actually it boils down to this picture that this mental picture. You're trying to fit this hyper volume, okay? This hypersurface that you're trying to fit. That's all. Okay? All right. So how do we do this? Okay, so here's where we need to do a little bit of math, right? But I'm going to just skip over this very quickly, but let me just skip this. So the thing that you do need to remember is that we are doing this in what we call a probabilistic framework. Okay, all statistics and machine learning is all based on probability. Okay, so basically here I'm trying to find a function, right? That blue curve that I showed you before, right? Find a function f that maximizes the probability, right, of seeing this data, right? Basically, condition on x and y, given x and y, which function will give me the highest probability? That's what I'm trying to find, right? So it's an optimization problem, right? It's really just an optimization problem. I'm just trying to find the maximum of that, right? So now, if you have a space of all functions, all possible functions, right? This is probably too big of a space, right? So what happens is that there's actually many functions that can fit the data with 0 error, right? For example, you could actually fit the data with 0 error with this function, right? But you could also fit it with 0 error, with this function, right? How about this function, right? And you can also fit it with that function too, right? There's actually many possible model that actually fit the data with 0 error. But what you don't want, those models are actually not good because they actually are overfitting, right? Because each one of these data points probably have some noise in it, okay? Measurement noise. And if you actually fit that exactly, you actually fit in the noise as well, right? Well, so what that means is that because noise, by definition, is not predictable, right? So when you actually apply to predict in the future, it won't do as well, okay? So if you actually try to fit the noise, you fit into the noise, right, and you can't predict the noise in the future, it's actually going to do a bad job in the future. Okay, so that's called overfitting, right? Okay, so what we do is that we basically pick what we call a model class, right? This class of function that we're going to use to fit this data is parameterized by some parameter theta. Okay, so this is basically the space of all the parameter theta. So this the objects within this space are functions. They're wiggles and stuff like that. They're ugly-looking functions, right? But here, it's actually a space of parameter, right? So for example, you have the space, so this could be a space of all the lines, right? So a line has 2 parameters, a slope and a y-intercept, right? So it has 2 parameters, a and b, right? Ax plus b, equals y, right? So this could be A and B right here, right? So this is the space of the parameter. But this objects within this function space are all the different lines that you could think of, right? All the possible different lines. So that space is actually very hard to work with, right? So what we do is that we work in the parameter space, right? So we work in that parameter space because that is actually much easier to work with, right? So we actually train the data, right? So each possible line here actually have an exactly one-to-one correspondent with one parameter in that parameter space. Okay, every function here, right, has one parameter, one set of parameter. Okay, so when you actually try to fit the model, what you're trying to do is you're trying to find the function. Instead of finding a function here to maximize that probability, you can simply find the parameter that maximizes, because every one of these parameters corresponds to one function. Okay, so computationally, you will work in this space. So that's why when we say we train a model, right, we're simply trying to find a parameter that give you the best model, right? And the best model is the one that fits the data, best and also predict the best. Okay. Okay. So let me just move on a little bit. So let me just skip this. Okay. So now once you get the model, how do you know it's correct? How do you know it's right? how do you know the model is actually right? You have to do something called, there's another step that data scientists often go into, is called validation, model validation. And one framework, one approach that we do use very often is what we call prediction on unseen data, right? So, remember what I said about, you can't just brute force remembering every photo that you see of a bird or plane. Because if I give you a new photo, you would do poorly because you've never seen that photo before, right? So you have to be able to generalize. And this validation is a process of test that generalizability. How generalizable is your model, okay? So what we do is that we take your data input and we split it, say 80-20, could be 30-70 or 60-40, right? Depending on how much data you have. And then we take that output of the system and we split it, 80-20 as well, right? So that 80% of that data, we actually use this 80% of data and 80% of the output, right, to the system to train the model, right? And then we actually test it on this validation, this 20%, all right? So basically what you're trying to do is, again, you're trying to find the parameter that maximize your training data, maximize the probability of seeing your training data, right? That's all it really is, okay? So you work in the parameter space to optimize the probability of those parameters. And since every one of those parameters corresponds to a function, what you get out of it is actually a function that maps the input to the output, okay? Right, so basically you take your training data, put them in there, take these are both the input and output of the system become the input of the learning algorithm, okay? So they both go in there, and then you actually find the parameter that optimize this. This is just an optimization problem, right? And then what you get out is a parameter, right, that optimize this probability. And you can actually go back and look at which model correspond to that set of parameter, right? So that model here, F, right, you can actually test it. You can actually take this data that you never used to train the algorithm, feed them in there, right, to produce a predicted output. And now you can actually compare that predicted output with the real output, right? Because you have this. You have this actual output, right? And this is actually a model prediction. So when the error between this one and this one falls below a certain threshold, then you're done. Okay? If the error between those two, right, the accuracy is not good enough, then the data scientists have to do more work. They have to do, for example, engineer a better feature or train it with more data and so on, right, to get this error down, right? So this is the final test, right? If this is below a certain error threshold, then you're done. Right? You have a model, right? And this model is parameterized by this data, this parameter, right? If it's a line, then you will have an A and a B, right? The A may be 2, the B may be 3, right? Whatever number that may be. Okay, makes sense, right? So a little bit abstract, but nothing you can't handle, right? Right? Okay. So let's take a look at. So that's how supervised learning works. Okay, supervised learning. Now let's take a look at reinforcement learning. So reinforcement learning, essentially, let's come back to this picture, right? There's no more, I would say, the system here, right? Because this actually is the environment, or what we call the environment. Then there's actually not really any input and output either, right? So basically, the learning algorithm is generating some action, and then the environment is producing some kind of feedback, whether it's a good or bad, right? So for example, if you are building a pricing algorithm, right? If you price it right, if you generate a price and you feed it to the environment, and the environment, nobody buys the product, right? Then it's probably pricing too high, right? That's a signal from the environment, right? If you price too low, right, then the feedback will be maybe too many people actually buy, right? Then that actually tells you, that feedback actually tells you how to adjust, So basically, actions are basically generated from this the balance between exploration and exploitation, right? So you could always exploit what work, okay? For example, if you know a price that works, right, you could price at that price, right? Or you can actually explore something beyond that you never tried before, because you never know what you haven't tried will not work, right? So you always want to reserve some probability to explore things you never tried before, right? So this exploitation and exploration is a fine balance. Okay, you have to very carefully craft that, especially at the beginning of the learning algorithm. You want to actually spend more time exploring. And when you actually explore a lot of things already, right, then you can actually explore more and explore less. But you never want this exploration to go to zero, right, essentially, right? Because you never actually could explore everything. If you're actually able to explore everything, then yeah, you could turn to zero. But the input space is typically a lot too big for you to explore everything. So you want to always have some probability of exploring something new. All right? Okay, so this is the learning algorithm, right? So basically now, these actions that the machine actually generate, right, and the feedback that the environment provides, both of these become the input to this learning algorithm. Now, essentially, now this output of the algorithm is basically the model. This model is basically updated with every feedback. Every time you use this model, it's actually feeding back to update this model. Okay, so this is actually how reinforcement learning works. Right, so reinforcement learning is really, think of it as just learning by trial and error. Right, you can actually try it, test it, see how the environment responds. If it works, great. I'm going to exploit that a little more. Okay, I'm not just going to do. If it works, I'm not going to just use that all the time because then I never know what I haven't tried will work or will not work in the future. Right, so I will exploit that a little more, but I will also explore other things that I have never tried before. Okay, so essentially, reinforcement learning is just, learning by trial and error. Okay, so now you know a little bit about two, I would say, very popular learning paradigm, right? The supervised learning and reinforcement learning. But as I said before, these are the probably the two most very common ones. But there's actually many learning paradigms out there, and there's new ones actually being created every day. Okay, academics, this self-supervised learning is actually the cutting edge today. That's actually what they use to train generative AI, such as ChatGPT. Okay, so today, what do data scientists do, and what do they do well, right? So as you can see, data science, right, it actually involves, getting the raw data. That's the first step, right? Step number one. But that actually looks, the actual work looks like just data generating, right? It's actually a lot of plumbing, cleaning, and generating of the data. And that actually requires a lot of, I would say, just computer science, just building the pipeline, right? And from raw data, you have to turn them into informative features, right? Informative features are information that you derive from the raw data that help you solve the problem better. And that actually typically comes from domain expertise, people with some domain expertise, right? You can't craft these informative feature without talking to someone who knows the business really well, okay? So typically that's actually required there. And turning this data into a model, that's just doing some math, right? Essentially, it's some kind of optimization problem at the end, right? Either maximizing the probability of the data, given the training data, or something else, right? Okay, so if you actually Google a little bit and see what data scientists actually do, right? One thing that they have to do is also communicate. So when they actually doing this also require some domain expertise as well, right? So today, if you were to grade a data scientist, how well they do in each one of these areas, turns out that a lot of data scientists are pretty good at doing the computer science and the math and statistics. What they don't do very well is the things that actually require a lot of domain expertise, because those are things that you can't actually learn in school, right? They can't teach you that, because every problem, every domain has a specialized set of features that they use, and it's actually problem specific, right? A good feature to solve one problem may not be a good feature to solve another problem, right? So these are very, very domain specific. Right, so you probably have heard that data science is the intersection between computer science, math, and statistics, and some domain expertise. And now you know why. Okay? Now you know why. So early on, I would say data science is really the intersection here. But because what Harvard Business Review said about data scientists being the sexiest job of the 21st century, everybody wants to be a data scientist. Right? So today, it's more like the union. Anything that you do that involves data, people can claim that they're data scientists. So it's a little bit confusing nowadays. So, but that is what it is, right? And if you actually look at how these actually maps back to the 3 layers of data science that I talk about, doing the computer science essentially is most of the work in the infrastructure layer. Okay? And building the model, the algorithm, is a lot of the work of doing the math and statistics. Okay? And the domain expertise actually is involved in the decision science layer. So now everything starts to fit together, isn't it? Right? You can see everything kind of fit together, right? Okay? So now you actually get a master of machine learning. Okay? Congratulations. So we can actually move on to the next topic, which is AI. Okay? So, all right. So I think the best way to understand AI is to see how AI came about. Right? AI actually evolved from BI, okay, surprisingly. Right? So now BI actually, I'm sure most of you have a lot of experience with BI, right? So if you actually have any data that you actually look at, right, you've seen BI before, right? So let's just take a look at a simple example, right? So these are stock trading symbol data, right? So when you have lots of data, so much data that you cannot look at every single data point, what would you do? You basically try to summarize it, right? You basically compute some kind of trend, some kind of indicator, some kind of index, right, to summarize the data so you don't have to look at every single data point to know what the data is actually doing, right? So this is actually just descriptive analytics that we've seen before, right? And one of the beauty of having I would say, these data, right, it's that you can actually build a model for it, right? You could build a model that also summarizes these trend of the data. But what's the advantage of having a model? Having a model means you can extrapolate to areas where you don't have data yet, right? Okay? So in this case, I'm extrapolating in the time domain, right? So if I extrapolate in the time domain, I'm doing the forecasting, right? But this is really just predictive analytics, right? If I could extrapolate in other domain as well, it doesn't necessarily have to be time, right? And now, if you have the ability to see the future, what can you do? You can actually start to tell people what to do, right? If I know it's going to rain tomorrow, I tell you to bring an umbrella. If I know earthquake's going to happen, right, then you tell people to build bunkers or something like that, right? So that's going from predictive to prescriptive. I'm starting to prescribing actions for people to do, right? So this, I would say, progression from descriptive to predictive to prescriptive is actually the evolution of BI. Okay, BI have basically started with purely descriptive, right? It's just summarizing data that you have, to essentially predictive, right? Essentially using data that you have to make an estimate of data that you don't have, to prescriptive, where they actually start to prescribing action for you to take. Okay, so now the question is, what next? What's next? What comes next, right? So now to answer this question, we have to understand what is the role of BI. What do BI do for business? What do they do for business? We call BI a passive decision support role, right? What does that mean? Passive decision support means that it's helping you make decision, right? It's supporting your decision, but it's passive, meaning that it's not making the decision for you, right? Humans still have to make the decision at the end of the day, right? So humans still makes all the decisions. So regardless of what the data suggests, what traditional analytic suggests, humans always make the final decision, right? If you look at any of the example, right? If you look at, for example, say, I could use predictive analytic to show you the trend of a certain stock, in the next month, right? You decide whether you want to sell or buy, right? I could even use prescriptive to tell you that you should really sell this stock right now, and you should buy pros, right? But at the end of the day, you decide what to do, right? You decide what to do, right? And there's good reason for that. And the reason is because, traditional analytics actually have limited accuracy, right? They're not very accurate. So they're no match to human experts, kind of human brain, right? So, but this is changing, Okay, and has changed, over the course of the last, I would say, 50 years. Certainly, data volume have increased from the times of punch cards, right, to today everything's kind of on the cloud. I think in the future, the quantum storage will actually come out. That will be even enable a much higher storage volume, right, and compute power as well, right. So our understanding of the model also is a big factor, right. So surprisingly, we actually have a fairly good understanding of neural network about like 50, 60, 70 years ago, okay? So now, if you actually feed these data into the model, right, you get some results. So this accuracy of this result actually depends on three things. It depends on the quality of the data, right? If what goes in is garbage, you're still going to get garbage out, right? So nothing can fix that, right? And it also depends on your model quality, right? How good your model is. If your model is too simplistic, you actually make the wrong assumption, then your result's not going to be good, okay? And it also depends on compute power, right? So sometimes you can actually have a good model and a lot of data, but it won't ever finish computing, right? That's like telling you that, I could tell you tomorrow's weather, but it will take me 2 days to compute them. Not very useful, isn't it? Right? Right? Okay, so basically, so this is just history. I'm just going to go this very quickly. Basically, early on, right, we actually have a fairly good theoretical understanding of, simple neural network. Right? So this is actually, in fact, pioneered by Yann LeCun, Geoffrey Hinton, and Yoshua Bengio, who got essentially the Nobel Prize for computer science, the Alan Turing Award, for inventing these neural networks, and all the way back in I would say the 50s. Okay, so we have that understanding, and early on, the limiting factor is data, right? So we have data, but most of them are not digitized, right? So even if you have the data, we actually can't use them because they're not digitized, right? And back then we're also dealing with I would say very limited computing power. Back then we're still using like vacuum tubes to compute, right? But over the years, lots have changed, right? Certainly our compute power have changed, right? I mean, we move into transistors and we start to have personal computing computers, and there's few things to recognize is that like the data volume increases, the computing power increases, and also our understanding of the sophistication of the model also increases. But our understanding of the model increases more or less linearly, okay? It's more like a progression. However, the increase in data volume and compute power is actually increasing at an exponential rate, okay? Anybody know why? Anybody heard of the Moore's law, right? Every 18 months, your compute power almost double because you could pack, double the density of the chip that you make them, right? So the Moore's law basically tells you that this data volume and compute power essentially increases exponentially, where our human understanding of the model actually increases linearly. So what that means is that eventually they're going to, data volume and compute power is going to overtake our understanding. That will happen no matter what. Okay, that's going to happen, right? So basically, I would say, by the time we get to, distributed computing, right, we basically have infinite compute power, right? Because you could just distribute them to as many computers as you want, right? And, by the time we get to, 2010, right, we have big data, we have GPUs, right? So now we don't even have limitation on data, right? So we have virtually infinite compute power. We have virtually infinite data. So what does that mean? That means data scientists is really going to have fun, right? We can use as sophisticated a model as we want, right? We have no limitation, right? Because these are the things that limit the accuracy of the model that we can use, right? So now the question is, if these models are so good that they agree with human experts pretty much all the time, do we still need to have the final say? Do we still need to make the final decision? Yes or no? Yes? No? Okay. So this is actually a heavily debated topic, because right now it's it's kind of, from time to time, I've seen kind of people swing one direction and the other, right? So, but keep in mind, economics comes into play, right? So basically, there are people who said that, yeah, we need final decision. But then there's some startup, going to say, I don't care, I have very little to lose, and they're going to use AI to automate everything, right? And guess what? They're going to outcompete those companies who have human in the loop, right? And then what are you going to do? You force to give up some of those control, right? Because they're going to be able to operate their business thousands of times more efficiently than you do, right? So it's actually a hard debate, right? So no one actually has an answer today, and people kind of swing between the two from time to time, right? So what comes next is really just the inception of AI, okay? So what's next is what we call this inception of AI is really the ability to automate decisions and execute subsequent actions, okay? So that's the inception of AI, just the beginning, okay? It's not true AI yet, right? Because, so basically, as I said before, right, going from data to decision to action, that is a human's job, right? We do that. Regardless of what the data actually suggests, we always decide what to do. We have been, right? Up to now, I would say, right? So, but if you actually are having data driving the decision and driving the action all automatically, then you have the inception of AI. You had the beginning of AI, right? So this is, already here. For example, with algorithmic trading, right? People who are in the investment world, right? If you could trade automatically, right? That's actually better because, in fact, for example, if your algorithm figured out that now is actually the best time for me to trade certain portfolio of my stock, right? It may send me a notification here, but then I'm talking. I can't actually go and push the sell or buy button, whatever it is, right? So I have to wait, right? I have to wait until I finish this talk, and then I go click that button. What happens then? The conditions have already changed, right? It's no longer the optimal time to actually buy that stock, right? So in fact, it's actually more optimal that way. Same thing as I would say, automated loan origination, right? So if someone meet the criteria, just give them the loan, right? In countries like China, or they actually are able to use the phone, various features of a phone. For example, like how fully charged your phone is, or at what point do you recharge your phone, right? These are behavior features to determine, your credit worthiness, okay? A little crazy, but that's what they do, okay? So, okay? So going back to the examples of the geospatial domain, what is the simplest, the most common prescriptive analytics system? Yeah, the GPS navigation system, right? So why tell me how to get home? Why not just take me home? Okay? So it's automating those decisions, right? You could tell me what to do to get home, but if you're executing those actions for me, right, then you're automating those decisions and actions, then you had the inception of AI, okay? But the problem is that automation is actually not enough, right? Automation alone is not sufficient to be an AI, because we have automation forever, in these factory assembly lines, these are perfectly good, okay? So that's another alarm. So another 10-minute break, okay? So now it's 3:45, come back at 4:45, okay? I know there's some people coming up here for questions, any questions? Yes? Can you use the mic? Yeah.
So maybe I'm just not thinking about this right, but when you're talking about reserving, 20% of the data for testing later, is there a way to make a model where you actually use that, you kind of make two models to essentially hold back data on both sides, like from that 80%, you would be holding back some for your second try, and then you can correlate the models, so that way you're using all your data?
You wouldn't use all your data, because there's always some, I think if you use supervised learning, typically you do want to reserve some data, right? And that reserved data can actually change, right? So typically, especially with time series, right? So for example, you always use say, it's like weather prediction, right? So you use like the last year's of data to train your model, right? And they actually use that to predict the next week of data, something like that, right? So that as you move forward, that window actually move along with you, right? So you always use like, so let's say you have 10 years of data, right? You use the first 9 years to train, and you test in the last year, right? But time moves on, right? So every kind of year that you move on, that last 9 year move on as well, right?
Does the model need to keep changing then? Okay.
Yeah, that's in fact the point of AI, which you'll hear very soon, okay? Any questions? Yes?
Question. I'm really interested in the ethical questions around use of AI. So GPS navigation is not really an ethical issue, but there's all kinds of decision making that if we just let the machine decide, potentially it's going to make judgments or outcomes simply based on data, not necessarily on the type of society in which we would like to live.
Yeah, that is actually a very challenging problem. So I'm actually, I work with a lot of the ethics committee, and I'm almost like part of my job is almost like an ethicist, because you do need to consider the impact of these type of technology in people's life, okay? So one of the big issues is with bias, okay? So bias is actually going to be present, right? Your data is never going to be 100% clean, right? So this is actually one of the problems that we've seen, even with ChatGPT, it's actually generating results that are, biased sometimes, and there's no guarantee to make, what's going on here? Okay, there's no guarantee that they will be totally unbiased. And so I guess the question is, how do you reduce that bias or mitigate that bias? So typically, there's several approaches. One is actually just clean the data before you train it, right? So that's actually, I think that's a lost cause, right? I don't believe that you can ever clean enough data to train an AI model that's totally unbiased. What I do believe is that you need to actually go earlier in the data generation process. A lot of the data that we use to train the AI today are generated by us, okay? So in order to produce AI algorithms that are less biased, we have to behave in a less biased way. Okay, so how do you do that? So you can actually use the feedback to guide human decision. Okay, so for example, a lot of the bias examples or documents have been documented are around HR, right? I use AI to help me determine who to hire, right? So if you use AI to help you determine who to hire, right, and you actually hire, in an unbiased way, right, it's actually very hard for you to actually see that bias in a few examples, right? So it's like if I have a coin, right, I'm not going to tell you if it's biased, right? But if I flip it 10 times, right, can you tell if it's biased or not? If it with 10 times, it's actually very hard, right? Unless it's all heads or all tails, right? It's not very easy, right? If it's like, if you got 6 heads, or 7 heads, right? It's very possible due to statistical fluctuation that you may get something biased, right? So bias is much more observable when you're looking at a large sample, right? At a small sample, right, it's actually very hard. So if you're a hiring manager, you're hiring, right? I'm only hiring 2 people since my started this career here, right? How can you say that I'm biased? But if you actually let this hiring manager see that, all the hiring managers before you in the last 5 years, you've been hiring all males, 25 to 35 or something like that, then it's very telling, right? Maybe you actually, try to examine more female candidates or something like that, so actually to change the human behavior is actually the fundamental, I would say that the real way to solve the root cause. Because I think a lot of these problems, people think that it's a data problem. It's not really a data problem. It's a human problem, okay? The reason that AI is biased is because we are biased, and it's reflected and amplified much more in data, in AI system, because AI actually look at so much of our data, right? So each one of us may be just a little bit biased, so little that we cannot even feel it ourselves. That's like flipping a coin, right? A biased coin, 5 times, 3 times, right? You're not going to be able to tell if it's biased, right? But if I look at all the humans' data, right, together, right, that little minute bias between every one of the human, right, they get essentially accentuated and magnified and become much more biased. So, but you can actually use that as a guide to tell human to guide human to change the behavior. Okay, I mean that's a big topic. I don't think it does justice for me to just answer that, but just illustrate some examples. I've written around 3 or 4 articles around how to deal with bias, and certainly happy to point you to that. And there's actually a lot of work being done. Yeah, and we don't have a solution to that yet. No perfect solution. There's some, I would say guidelines, right? So for example, the hiring example, right? If you are using a AI to help your HR to hire people, right? Then it's actually not very, I would say, effective to say that I'm trying to get to unbiased. So very often, people say I have an ethics committee, right? So I'm going to use algorithm in an unbiased way, right? That's actually a lost cause. It's actually not very achievable, and when people don't achieve it, they actually give up. Okay? So it's actually, so whatever it is, right? Like I said, AI is biased because we are biased. So look at your current state. If your current state, your hiring practice is, say, I don't know, very biased, say just as an example, right? Say you're hiring 80% male, 20% female, something like that, right? Then obviously that's very biased, right? You don't want to say that. We want to get to 50-50. That's a lost cause, right? Get to 70-30 first, right? And then get to 60-40, right? Baby step there, right? That's how you get results. So, okay? All right, looks like we get people back. So, all right, so sorry, I'm eating a cough drop because my throat is starting to dry up. All right, so as I said before, automation alone is not enough because we have automations since the time of assembly line, right? So what's wrong with this assembly line? What's wrong with this assembly line? So the automation there, right? Basically, so this looks like a car assembly line, right? It's trying to put together a car, right? So if you have some, I don't know, some robots that tries to screw on a tire or something, right? So what happened if a tire becomes misaligned? The robot couldn't do anything to it. What happened? The human have to stop the assembly line, right? And then what do? They go and align that wheel bearing, right? And then they restart the assembly line, and then everything goes, right? Now, what happened when at a later time, the wheel bearing become misaligned again? They have to basically stop the assembly line again and go realign again, right? So that's the problem, right? This is not a very smart system. You never actually learn, right? You never actually learn to say, oh, all I have to do is just realign that wheel bearing a little bit, and I would be able to screw in that screw, and then I could, I don't even have to stop the assembly line, right? So the key question to ask right now is what makes AI intelligent, right? So if you actually do a little bit of a Google research yourself, you probably have seen this diagram before, that deep learning is a kind of machine learning, and machine learning is a kind of AI, right? Anybody seen this picture? Yeah, a lot of people have seen this picture. This picture is very popular. It's actually in Wikipedia, okay? However, it is actually not quite correct, believe it or not. So it's not completely wrong. So it's actually, there's a reason Wikipedia did not actually take it down. It's not completely wrong, but it had to be interpreted very carefully, okay? So in fact, deep learning is a kind of machine learning. However, machine learning is actually not a kind of AI. But the reason that they put machine learning inside AI is machine learning is actually part of every AI system, okay? It's actually used in every AI. It's just another example that I'll give you is that for example, this V8 is actually a kind of engine. It's V-shaped 8-cylinder engine, everybody work on cars, right? Okay, so you know what V8 engine is, right? It's a kind of engine, and the engine is actually used in every car, okay? Now, if you don't have these boundary conditions here, right, it's very easy to come to the wrong conclusion that an engine is a kind of car. And you know that engine is not a kind of car. That's stupid, right? Right? That's ridiculous, right? So that's the kind of, I would say, cautious you need to have, right, to interpret this diagram correctly, right? It's actually, yeah, so this diagram I think is sometimes very misleading, right? So I would just like throw away and, yeah, just let me give you a better diagram, okay? Now this better diagram, starts with big data. Now big data is turned into model by data scientists, okay? That's why the human is there. Now what do data scientists use to turn data into model? Machine learning, right? Good, you guys, somebody is paying attention, right? So remember, machine learning is a process of turning data into model, right? So data scientists use machine learning to turn data into model, right? So there's lots of machine learning algorithm. I could fill up several more pages of these names that would just confuse you. But important thing to know that deep learning is, in fact, a kind of machine learning, okay? But machine learning, as you will see soon, is not a kind of AI, okay? So now, this model, once you have a result, you actually, somebody have to look at that result and decide what to do with it, right? So some decision have to be made. And in the business world, this usually boils down to some kind of action, right? Some decision and some action you have to take. And then the action will actually drive some outcome. And typically, this outcome will be fed back into your analytics system in order to drive, I would say, better performance. Now, as I said before, right, human always make the final decision, right? Regardless of what the results suggest, we look at those results and we make the final decision, right? So that's why we're here. Now, for the actions, right, I mean, today I would say that a lot of actions in the digital world can already be automated completely by machine, okay? Because what does it involve to execute an action in the digital world? You just have to execute some code, right? just execute. So that's actually very easy, right? So in the physical world, right, because robotic didn't advance as quickly as I would say software, So a lot of the physical world actions, they still need to be performed by human, right? But even that's starting to change, okay? So with robots and Boston Dynamics, seeing the robot be able to do a backflip, that's pretty amazing, right? So now, feedback here traditionally is also collected by human, right? And we use a survey essentially to kind of collect these feedback. And this is obviously not very efficient, very, very slow, right? So now, this feedback in the ideal case, they need to be in as fast as the decisions are being made. Okay? So for example, in a driving case, right? If you are driving a car, you are making decisions in real time, right? In real time. So now let me ask you guys, what is the feedback to you in this prescriptive analytic system, the GPS navigation system? What is the feedback to you? It's actually that blue dot that shows you where you are. Right? That's your feedback, right? Right? That tells you every second, every minute, every instance, right, where you are. That's your feedback. Now imagine how good this GPS navigation system would be if that blue dot updates itself with a minute delay. Your GPS would be useless. You get into an accident, you probably hit some trees or some pedestrian, right? You say make a right here, and you say that there's no road here, right? So a minute may not be very long, but in the situation where you need to make real-time decision, it's ages, okay? Now, how quickly this actually need to feedback is really essentially determine how quickly this decision has to be made. Like for example, if you're running a marketing campaign, right, and you course correct your marketing campaign, say every week, right? Then basically this can be, feedback can be, say a few days or up to a week. It cannot be longer than a week, right? Because if it's longer than a week, then there's the same problem with saying that I'm going to be able to tell you tomorrow's weather, but I'm going to tell you 2 days later, right? That's useless, right? So, right? Okay. So the first thing we need to do is that we need to automate this feedback tracking, right? And that's actually very easily done today, right? You just have to have some engineer instrument some code, right? And with today's, I would say, even with in the actual physical world today, with sensors and IoTs, it's actually very easy to write code to track this kind of feedback, even in the real physical world today. Okay, so now one key point is that if this model here is actually good enough, this model here, if it's good enough, right? Big if, okay? If it's good enough, then we can automate this decision here. Okay? Why? Why do you think that's the case? If it's good enough, what happens? Remember when I say a model, okay, let me step back a little bit. Maybe you may ask, well, how do I know the model is actually good enough? Right? How do I even know if a model is actually good enough? Accuracy, according to what? Yes, but how do you determine what the accuracy is, right? Basically, the model is good enough, yeah, if it matches a human expert's decision pretty much all the time, okay? If it's able to match a human expert's decision, right, pretty much all the time, then it's good enough, right? And how good is, I would say, how much is the matching the human expert's decision is domain specific, right? For example, if you're running a marketing, this is a marketing prediction, 80% is probably good enough, right? If this is a medical diagnosis system, right, then you better match a human expert's decision 99.99999 times, right? Okay, so yeah, so what that criteria is domain specific, right? It has to do with how much risk that you want to. You're taking, right, when you actually let that decision being automated. So if this model is producing results that match a human's decision all the time, right, then the accuracy is pretty high. Right? Basically, the human experts actually providing that validation, that test, right, that you benchmark against. Right? So if this matching a human expert's decision pretty much all the time, why do you still need the human to have the final say? What will happen to that human when they actually have the final decision? Basically, he will be saying, I agree, 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 pretty much all the time, right? Because it's matching your decision pretty much all the time. So why do that? Why not just let the AI automate it, right? So if you let the AI automate this, right, then this actually could go much, much faster, right? So when you actually have this, say in the digital world today, right, basically everything here basically can be automated by machine, except in the rare cases when machine actually disagree with human experts, right? And that's why I still have that little sliver of yellow there. When machine actually disagree with human, you could still override, right? Human could still override, right? It doesn't mean that you have to follow it all the time, but most of the time when it's actually confident, you should just let it automate it, because why saying, yes, I agree, go execute over and over again, okay? Right? So now, if you are able to automate this loop here with almost no human intervention, except in the rare cases when human and machine disagree, what does that mean? There's actually two implications here. One is that this loop can go very, very fast, right? Because we are the slow one, right? So if we are out of the loop, right, then this loop can go very, very fast, right? And the second one is that if everything can be automated by machine, that means everything can be tracked and turned into data, right? You can actually turn that into data, and you could actually put that into your big data store again, and then basically now if you run your machine learning again, you get an updated model, okay? Where we're asking about the model being updated, right? This is how you update your model. The more, every time you use it, right, these data about the decision you make, the action you take, and the outcome, right, get fed into your big data store, right? So now, if you actually feed them through your machine learning process again, you have a new model. And guess what? This model, do you think is going to perform better than the previous one? Yeah, most likely you will do better than the previous one because it has all the data before plus new data, right? So, okay. So now this actually, I would say, it's very wise to do this semi-automated, right? I mean, you could do this completely automated, and that's actually not advisable because machine, believe it or not, learn stupid things, okay? They learn things that are actually wrong, okay? And maybe illegal or unethical, right? So it's actually very good to monitor what's going on, what they actually learn, what they pick up, and the feature that they learn, the feature that they discover, and that's actually all important, right? So Now, basically, if you keep in mind that if you actually use this system over and over again, right? Every time you use it, you get new data that actually goes into your big data, right? And you actually get updated model. So every time you actually use the system, the model gets better. Every time, right? Every time you use this model, the model gets better. Okay? So eventually, this model will be a very, very good model of this process of going from decision to action to outcome. It's going to be able to determine what kind of action, what kind of decision you make is going to have what kind of outcome. It's going to be a very, very good model. And this is what we call the learning loop. Okay? It's the feedback loop that enables AI to learn and become smarter. Okay? And this is a highly, highly simplified architectural diagram of any AI system that you can see. Okay? And guess what? Machine learning is a part of it. Okay? Machine learning is used in this AI system, but machine learning is not a kind of AI. Okay? If you just have this machine learning, right? A lot of people often will say that, oh, I use deep learning to build my model. Okay? What you have is just a very, very smart model to begin with, but you never actually get smarter if you don't have this learning loop, this feedback system. Okay? So that's the learning loop, right? So now we can actually define what AI is, okay? Now this is something that you're probably waiting for, right? So now the definition of AI, I would say, changes over time because AI actually has been around for a long time. So some people literally said that AI is whatever a machine can do today that it couldn't do in the past. There's some truth to that, because back in the day when optical character recognition was created, they think that's AI because this OCR, this program is able to recognize, prints. It can recognize handwriting, not only my handwriting, but yours, his, and everybody else's handwriting, right? So people back then think that was AI, right? But today, your phone could do this. Your phone could basically do OCR, right? Nobody thinks that's AI anymore, right? So just take this definition with a little bit of a grain of salt, okay? So, but in the, I would say, recent, maybe half a decade, I would say, this definition probably will still be valid, right? So AI is really just a machine mimicry of human behavior with two important characteristics, right? It's able to automate decisions, right? Automate decisions and also subsequent actions, and it has to have the ability to learn. Okay? It has to have the ability to learn, and what that means is that you have to be able to improve its performance with usage. The more you use it, right, the better it gets at what it's doing. And that's through that learning feedback loop, okay, that you have. Because every time you use it, it generates more data. You can feed in your machine learning algorithm to produce a better data, better model, right, to make better decisions for you. Okay? So, yeah, just because you use deep learning to build your model doesn't mean you have an AI, right? So, okay. So remember all these verbs that are associated with different kind of analytics, right? Descriptive analytic, just summarize data. Predictive analytic, use data that you have to estimate data that you don't have. Prescriptive analytic, they just optimize, right? Now, AI is actually not defined by one verb, but two verbs, right? It has to be able to automate and it has to be able to learn. That's it, okay? Simplest way to look at AI, okay? All right, so now this learning ability is what allow business to adapt, right? Who is this? Anybody know? Charles Darwin. What's his famous quote? A lot of people think that it's survival of the fittest. Right? His theory is evolution, but his famous quote is actually not survival of the fittest. Okay? Yeah, he says it's actually, this is his quote. Okay? It is not the strongest species that survives. It's not even the smartest species that survive. Okay? It's the one that's most adaptable to change that actually survives. It's adaptability. That's key. Okay? And what this learning, this ability to learn is what provide company the ability to learn from the market. Okay? Through data. Okay? So they can adapt to the market much faster, much better. And they're the one who's going to survive. Okay? So we've seen this in evolution already, right? Basically, people who actually built a really, really smart algorithm, say like, I use deep neural network to build this very, very smart algorithm, right? You may just be very intelligent in the beginning, right? So you may beat all your competitor for a while, but as the environment changes, if you don't learn, you're going to be obsolete. Okay? So this adaptability, the ability to change and update this learning from feedback is key to AI, right? So this is actually how, the program, AlphaGo is able to beat the world champion in the game of Go. Okay? Everybody heard this story, right? Why do you think that is able to do this? Because if you look at it, AlphaGo is a program written by a human, right? And none of those humans are as good as this guy, because he's a world champion. He's the best guy in Go in the entire world, right? None of those programmers who programmed this AlphaGo is as good as this guy. So how do you think AlphaGo is able to beat him, right? It's actually learning from playing against himself. Okay, so this is where the speed argument comes in. Remember there's two implications. When you actually train the AlphaGo program to be good enough to play against a human, what happened is that they actually let AlphaGo play against a different version of AlphaGo against himself. Okay, so somebody will actually win and lose, but then they actually learn from that and never make those mistakes again. Okay, so if you look at a lifetime, how many games a professional Go player can play in their entire lifetime? How many games do you think a professional Go player plays? Probably tens of thousands, right? If you're very productive, maybe hundreds of thousands, maybe, right? But that's nothing for a computer, right? A machine, AlphaGo could actually play 1 million games in a matter of weeks, right? So what that means is that they can actually make all the mistakes that this guy makes in his entire lifetime, probably 2 or 3 lifetimes, and learn from those mistakes and never make those mistakes again, right? That's powerful, right? Iterating quickly and adapting is actually what makes you smarter, okay? So now the next question is a lot of people often ask me, well, I know what AI can do for me, but what can AI actually do for my business? Right? So I think that's actually a wrong question to ask, because by now, most of you probably would know this already, that AI can pretty much do anything that we do, as long as we can digitize it fully, okay? Because what do AI need to work? It needs training data, right? If you could digitize a process completely, then you will have enough data to train an AI to mimic what humans do in those situations, right? So the real question that business should really be asking is, what can you digitize? Because whatever you can digitize, you will have the data to train the AI, and the AI will be able to do those things, to mimic those things, right? That's what you do, right? So that's really the key that business have to ask, right? So now, there are lots and lots of, I would say, AI out there today. There's probably hundreds and thousands. I probably would not be able to name them, all of them. But there's actually 4 major applications of AI. Okay, and these are, I would say, probably will still be very relevant in the next, I would say, 5-10 years. Okay, so one is what we call perceptual AI. So perceptual AI is AI, sometimes also called cognitive AI. Okay, so basically they're trying to mimic the higher perceptual cognitive function of a human being, such as vision, language, and other perception, like speech and all that, right? So some examples of these are very famously ChatGPT, but also just Google Assistant. Even Siri's on your iPhone is a perceptual AI, cognitive AI. Okay, so what is the biggest applications of these perceptual AI? They are in human-computer interaction, right? And that's actually a no-brainer, because if a human is able to interact with a machine that could see the world as they do and could speak their language, so they don't have to talk to them in code, right? Then obviously you have better human-computer interaction. You can interact with the machine a lot better, right? So that's perceptual AI, also AKA cognitive AI, okay? Next class is, I would say, internet AI. So internet AI is called internet AI because it is trained on data that we left behind when we surfed the internet. So we left a lot of digital footprint behind when we surfed the internet. So those data are used to train these AI. And so I would say, typically, the biggest application of this class of AI is in personalization and recommender system, right? So that's why sometimes they're also called personalization AI, right? So this class, I don't think I need to tell you too much more about it, because every one of us probably experienced it. Everybody here has an Amazon account. I bought stuff on Amazon, right? Yeah, so, basically, they're one of the pioneers of this type of AI, right? Basically, the recommender system that they actually created actually have a very, very long name that goes by the name of people who bought this also buy that. Right? So that's the name of the algorithm, right? So yeah, so basically, if you buy what they recommended, then the learning feedback loop says, give them more of the same stuff. If you recommend some stuff that you didn't buy, then something needs to be adjusted, right, to recommend some other stuff, right? So that's where the learning loop comes in, right? So no need to explain that anymore. Another class that's actually very, very important in the coming days is autonomous AI. So autonomous AI is the AI behind the self-driving car, okay? So today, the biggest application is the self-driving car, right? It's autonomous vehicle, right? So tomorrow, I would say it's probably a lot more. You probably have advanced robotics, autonomous drones, and other autonomous systems that can actually work autonomously, right? So that's why they call autonomous AI. The last class is what we call business AI. So business AI is, actually is the biggest, I would say, the most confusing class of all, because they are not used by consumers. Okay, these are actually AI that's used by highly specialized people, and then in a specific domain, in a specific role. Okay, so as you can see from some of the example here, right? It covers, like, for example, fraud detection, algorithmic trading, machine-aided medical diagnosis, right? So Watson actually do a lot of machine-aided medical diagnosis, right? And even like drug discovery, right? In fact, PROS is also a business AI, okay? And what kind of decision do we automate? Come on, pricing decision, right? So, right? Right? So pricing decision. So you also learn from that as well, right? So basically, so these are business AI. Sometimes they're called decision AI, because the biggest application of these type of AI is to automate business decision. That's typically made by some human experts previously. Okay. So whether it's an analyst trading on Wall Street, right, you could create AI to mimic that. Whether it is a pricing analyst that give you the price, you can have our AI help you build those prices for that, right? Or something else, right? Or even a doctor, right? Or something like that, or even a drug designer or something like that. So that's all possible, okay? All right, so that's the 4 major classes of AI. So you may ask, where is generative AI? Generative AI is actually not a classification based on business use case, okay? So if this bubble here represents all AI systems out there, right? We can classify them, categorize them by business use cases, okay? So you classify them this 4, internet AI, perceptual AI, business AI, and autonomous AI. So these are use case classification, right? But you can also divide them by the type of model, right? If you have a generative model underneath the AI, then you have generative AI. If you have a discriminative model, then you have discriminative AI. Discriminative is just a kind of model, right? So rather than the generative model, typically model the full probability distribution, whereas a generative AI only model the decision boundary, right? So that's a little bit of a data science jargon, but you could talk to me after that. But basically, if you actually, so basically, generative AI can be in any of those 4 categories, okay, depending on where you use them. You could actually use generative AI to help you, for example, in business AI, right? So we've seen generative AI as a chatbot, right? So that's perceptual AI, right? That we are very familiar with. But you could also use generative AI to help you create drug designs, right? For come up with protein drug candidates for you to evaluate, right? So in that case, that would be business AI, just because normally a business expert, right, a protein kind of drug interaction chemist would typically do that. But now you have an AI that's generating those designs, and now you could just go evaluate it, right? So it's not a classification based on use cases, right? So it can actually be in all of these use cases, right? Okay, you can even classify AI based on the level of intelligence. Now, one that's actually very, very popular is artificial narrow intelligence, artificial general intelligence, and artificial super intelligent, right? We don't really have that much artificial intelligence today yet. I mean, we definitely don't have artificial super intelligence. So in the future, this may be the classification, right? And again, it's not a classification based on use cases, right? It's classification based on the level of intelligence. It's just a different way to slice the pie, that's all, by different criteria, right? Okay? Easy, right? Okay, so now the question is, how can you actually pick the right AI in such a crowded market, right? So this is actually, I would have to say that, today, there are a lot of hype around AI, right? Everybody, claiming or saying that they have AI, and some of them may be true, but then you have to understand, does that actually help you? Okay, so one example is like, for example, if you have a technology company, right? If you have some kind of web technology, right? So you created some legacy business logic to address some business problem. You package it up and you sell it to business, big business. That's what technology companies do. In the Silicon Valley, there are lots of them. Where I'm coming from, there's lots of them, okay? So now, if you are to use a type of AI, right, which one do you think is actually the easiest to actually incorporate into your legacy business logic? To answer that question, you can actually look at which type of these AI actually have an abundance of training data, right? So these two AI, there's actually a lot of training data out there, right? Basically, you could just, to train the perceptual AI, you just scrape YouTube, right? Or, to train the internet AI, just, scrape some people's kind of, surfing data. There's plenty of data here, right? But on the other hand, here you actually have a scarcity of training data. You actually, so certainly, autonomous AI, their vehicles, like cars, are not made to collect data. They're made to bring you from A to B, right? So, right, today, I would say that a lot of the car manufacturers are starting to figure out that maybe they should start collecting more data, right? So in the future, this may change. But today, there's actually not a lot of training data for autonomous AI, right? But what about business AI? Business AI also, there's not a lot of, I would say, training data out there because nobody wants to share the business decision out for the competitor to find out, right? So basically, here, there's the scarcity data, but for two different reasons. One is because they're not built to collect these driving data, and the other, this business AI is because people just simply don't want to share their business decision data, right? So now, what about, there's another concept called transferability, right? So if the models up here are what we call highly transferable. Basically, if you train AI to, so for example, to speak English, right? You can pretty much do a decent job in any business scenario, right? It may take them a little bit of time to learn your business jargon, to learn your business domain, but you will do decently, okay? Same thing as the autonomous AI. If you train a autonomous AI to drive a four-door sedan, it's going to drive any four-door sedan pretty well, right? It may not drive everyone equally well because some, are bigger, some are smaller, some may have different features of the car, right? So you may have to learn a little bit, but you don't have to learn a lot. So these are, once it's trained here, it's actually highly transferable, right? These models are highly transferable. But the ones on the bottom here, they are very user-specific. These type of models are very user. So imagine this, right? If you have a internet AI, say a personalization engine that recommends my favorite food, because I like to eat food, right? How do you think it's going to apply for you? Nothing, right? It's not going to do you any good to use my model and applying that on you, right? It's going to recommend all the food that I like, but nothing that you like, right? Unless you happen to be very, very similar to my, the kind of, in terms of our taste is very similar. It's not going to help you, right? Same thing as business, right? So one thing that, if you train a business AI to essentially mimic how a business expert make decision in different business scenario, how do you think that AI is going to work for another company? It's not going to work very well, right? Aside from getting the intelligence of what your competitors do, right? It's not going to do you any good. It's not going to help you automate it. So these are highly specific, right? So if you actually look at it, this is the type of AI that has abundance of data and is also easily transferable, right? So very often, company, especially startups, right? They'll just like put these perceptual AI on top of their legacy logic, and they will claim that, hey, I have AI, and that's true. They do have AI. This is, perceptual AI, cognitive AI. They could claim that, right? But is it actually going to help you, right? So what do I say this perceptual AI, the biggest application is? It's human-computer interaction, right? Yeah, so as more you use it, what's going to happen? Remember, the more you use AI, they have to learn, right? They have to get better at what it's doing. So what is it going to get better at doing? It's going to get better at interacting with the user, right? So what that means is that it's going to be, I don't know, for example, understand your business domain, your business jargons. You may understand, your accent. You may understand your humor or your sarcasm or whatever. It's going to understand. But is it actually going to help you solve your business problem better? No, right? It's not going to solve your business problem any better, right? It will actually do a better job and make you more productive at solving those business problems, but it's not going to solve a business problem better, right? But the value proposition here is not to solve your business problem better. Here, the value proposition of a lot of these perceptual AI is increase productivity of the employees. Okay, when you use it, you can actually increase your productivity, right? So they do have a value proposition. It's just not, solving the problem better, right? On the other hand, business AI, the value proposition is have a better business decision, right? Because every time you actually use this AI, it gets better at solving your problem, right? So every time, for example, take say opportunity detection in our platform, right? It's every time you actually use it, it actually knows what kind of opportunity is better for particular sales. It's going to be recommending better and better opportunity for that particular sales. Maybe everybody wants to close big deal, but you actually, if you actually take a too big of a deal, maybe you can't close it, right? Maybe you actually recommend more appropriate deals for that sales, right? So these are the AI will actually learn and recommend more appropriate deal for that person, rather than just what he actually wants. Right? So, okay. So, but you can certainly kind of put these AI together. For example, you can actually put these perceptual AI on top of business AI, and that will give you better decision and also productivity increase. Right? So that's certainly good. Right? There's no problem there. But keep in mind, right? Now you know a lot about AI. Okay? You just have to think about it more critically when you're actually hearing people talk about these subjects. Okay? So, okay. So I boiled down AI into 4 major business applications, right? 4 major applications. But what can they actually do? What's the outcome they can drive, right? So again, every AI can basically drive a different outcome. But there's 3 main categories that I want to cover, right? One is improve customer experience, and the other one is increase efficiency. The last one is actually to help you improve revenue, right? Grow revenue, right? So which type of AI you would use depends on what you want to drive, what you want to accomplish, right? So if your goal is to improve your customer experience, for example, deepen engagement, boost conversion, and gain loyalty from your customer, which type of AI would you use? Yeah, perceptual, right? So, right, what else? Okay, because, if, So, I mean, personalization, right? Personalization, because if machine know what you like, what you prefer, you certainly will have a much better customer experience, right? So those 2, no doubt, right? Okay, now if your goal is to increase efficiency, right, to reduce costs, raise productivity, increase throughput, what would you use? Okay, here's a little bit of debate here, right? So this is actually, in fact, a very crowded market, okay? So this is, I'm come from the Silicon Valley. Basically, every startup there is actually, trying to make some kind of AI that fixes some broken or simply business process that just doesn't work. Okay, so basically, perceptual AI could certainly do that, right? It does that by improving productivity of your employees. If you actually apply it internally for your employees, right, it could improve productivity there, right? And certainly, autonomous AI could do that because autonomous AI, they're robots. They don't need to sleep, they don't need to rest, they don't need to, take the 10 minutes breaks between, so they can work 24-hour, 365 days a year. So much more efficient there compared to us, right? So, and certainly business AI as well, okay? Because making business decision faster also makes you able to run this business, business more efficiently, right? What about the last one? If your goal is to grow your top line, grow margin, drive profitability, what would you use? Yeah, business, right? Business AI, right? Better decision always lead to better outcome, right? So now, if you actually think about this a little carefully, right? I mean, in fact, every one of these AI drive every one of these outcome, okay? But some of them are less direct. Some of them are actually less direct, right? Because, if you think about this, perceptual AI can drive revenue growth too, right? But it's actually a lot of trickle down, right? Because you have to give the customer a better customer experience, and the customer have to feel, that they actually get a good customer experience, and they will continue the business, and as a result, they would drive your top line, right? But that's very, very indirect, right? The most direct, so these big dots actually represent the most direct effect of AI, okay? All right. So now let's talk about pricing, because pros obviously is pricing, right? So why do you think AI is actually so beneficial in pricing? Why is AI so beneficial in pricing, right? So one of the things is that, pricing today actually involves big data. I'm going to check my time here because it's almost 5 p.m., right? Can you believe it? You've been with me almost 3 hours, okay? So actually, almost 3 hours. So so today we have big data, right? We have big data. So now you have, for example, data such as competitor pricing, you have commodity index, you may have the weather data, you may even have consumer sentiment, even like social media trends and so on, right? Lots and lots of data for analysts to analyze, right? So if you don't use AI, right, your analyst is going to take forever to analyze them, right? It's going to take forever, right? If you have AI, basically you can just boom, and you're done. That's it, right? So AI can analyze this big data in near real-time speed, right? That's a huge, huge benefit, right? Another benefit is humans are actually very, very good at detecting these very dramatic changes, right? Rapid, dramatic changes that's episodic, right? That's kind of suddenly create something, right? For example, you could certainly see a trend right here, like these guys, right? There's something different there, right? But AI can pick up these. So this is, for example, someone increased the tariff, right, or something like that. This is obviously going to change the pricing, right? So, right. So obviously you're going to change your pricing based on that. But AI is actually very good at even detecting gradual and continuous changes, such as these guys, right? You may not spot that right away, but the pattern is there, right? So. So these are, for example, inflation, right? Inflation, maybe not in the recent days. Before COVID, inflation actually don't change that much, right? So it may be, changing just slightly, right? So if it's changing slightly, why not say increase your price a penny a day, and 365 days later you increase $3.65, right? Why not wait until a year later to increase $3.65? Why not increase a penny a day, right? So you can actually pick up this minute, slight changes that may be very, very hard to detect, right? So, so these are what AI can do, right? So on the other thing that humans are actually good at is that humans are actually very good at, I would say, getting the directionality of the price change correct. Right? I know that if there's a big storm somewhere, then the price, is in fact impacting crop. The price of crop, should increase because it's damaging the crop, and so it reduces the supply of crops, right? So I know that it should increase, but the question is, how much should it increase? Should it be 5%? Should it be 5.2%? Should it be 5.237%, right? So that quantitative precision is actually very hard to get at, right? So, so AI actually provides this quantitative precision down to the penny, right? So it's very precise, right? So, and moreover, AI actually provide consistencies over a long time frame and scale, okay? So very often, if you have a very experienced price analyst, right, they have priced hundreds and thousands of scenarios, right? They may remember that, 10 years ago, this similar situation happened before. Like, what did I do then? But then like, you may think that, I know I increased the price, but how much did I increase? Maybe I increased $2, or should I increase like $2.50, right? So you may not remember, right, what's going on there, right? So, but AI actually provides this consistency, right? So you have over long time span and large scale, it remains consistent, right? So AI actually provides, consistency, quantitative precision, ability to adapt to small changes, right? And capacity to handle big data in real time. So you may ask, what do humans do then, right? What do we do, right? What do we do, right? Humans are actually, I would say, a lot better at dealing with new and unknown, right? Dealing with the situation that, this situation had never happened before, right? So if you ask AI to price in this situation, they're just going to do a random guess, right? It's not going to do a good job, right? So you are there to kind of actually deal with these, right? For example, using new data, can you derive new features, right? Can you derive some new features that's actually more informative about your consumer's demand or something like that, right? So these are handle exceptions, essentially teaching the AI how to price in this new situation that they never encountered before. So this is going to be, I would say, the future roles of a lot of us, right? There's no stopping to AI, right? AI will disrupt every single business in every single role out there. In fact, the most heavily disrupted, I would say, roles are skilled workers' roles. Like, in fact, I would say a lot of people predict that data science will be completely automated. So I'll be out of a job before all of you do. Yeah, because this actually is very quantitative, right? I mean, if you have enough data to train AI to write code, write data science code, right? It's going to do it. Generative AI like ChatGPT can already do that today. So, you don't have to write code. You could just tell them in English what you want. So basically, some people said that English will be the most popular programming language of the future, because you could just tell ChatGPT what you want in English, and it would just translate it into code. So, right? Okay, so now the key thing to realize is that these jobs are probably more strategic and more important, and probably more interesting as well, right? A pricing analyst, the job is actually not necessarily fun. And likewise, some part of data science's job is not necessarily fun, right? Remember the part that I talk about data generating, cleaning the data and everything, right? So those things we'd rather have AI help us do, right? So we can actually focus on the higher value add, building relationship with our customer, and meeting their needs and all that, right? Okay. So finally, the last part, I do want to talk a little bit about how do you build and implement AI, right? So remember this definition: AI is a machine mimicry of human beings. It's actually mimicking what humans do, with the ability to automate decisions and learn, right? So let's take a look at an example. So this is the Android Pie, okay? Android Pie is released in 2018, I believe, okay? So they are saying that this Android OS is actually powered by AI for smarter, simpler experience that adapt to the user, okay? So let's take a look at one of these features, right? So this, if you actually, I don't know why this is so bad. So this is adaptive brightness, okay? It's able to, today, most of your phones, right? If you go out in the sunlight, it's going to be turn bright. If you come indoor, it's going to dim it down, right? So that adaptive brightness is actually an AI feature, okay? So let's see how that come up with that, right? Okay, so the screen brightness, right? Essentially, you can actually, it should be somehow correlated with the ambient light, right? If the ambient light is too bright and your screen is bright enough, you're not going to be able to read anything, right? So you detect the ambient light with essentially your camera, right? Your camera is essentially a sensor that actually detects what's the light level on the outside, right? So that, basically, it's a good way to tell your Android system, right? If the light level is high, I want you to turn the brightness all the way up. If the brightness is very dim, right? For example, midnight right here, right? I may not want to turn it all the way down to 0, but I just want to dim it down, right? So if you actually look at the data, what it actually look like, it may be something that look like this, right? The light level, so this is actually maybe the people's behavior data, right? So you could fit it with a line, right? You can fit it with a line. Right? Basically, you can actually build a very simplistic model, right? Just based on the light level that you detect, I could just turn the brightness corresponding to the corresponding level here using this linear model, right? It wouldn't do very well, but you'll do a decent job, right? So in fact, you can actually, what they find is that if you actually do just linear model, right, they could account for about 50% of the user behavior, which is not good, right? Which is actually very, very bad. So basically 50% of the user are saying that I'm not happy with the brightness level that you're adjusting to, okay? So how do they know that? Basically, when it is adjusting to a level that you don't like, what would you do? You change it, right? So basically, you go and adjust the screen brightness, right? And guess what? This is the feedback data. This is the feedback data that they use to essentially, to see, whether you actually like the brightness level that this AI recommended for you or not. Okay, so they're actually using this, right? So you may have one person, so this, Mr. Bad Eye. Okay, maybe you have a really bad eye like me. Okay, but he can't see very well, right? So basically, he's actually trying to turn the brightness level all the way up, higher than what the AI would have recommended, right? So every time the AI at this light level, the AI is recommending this level, he actually wanted to turn it brighter, right? That's what happened. That's what this data is actually showing you, right? Then you may also have this, another person who's very battery conscious, right? She wants to save battery. So every time the AI recommended a certain brightness, right, she will actually turn it lower, dimmer, right? For example, like this, okay? So below this line right here, right? So you actually, so what they find is that the engineers Google, they actually find that if you actually use a 4-point anchor, so this is a spline model, right? They can account for about 80% of the behavior. Human behavior. Okay, that means so 80% sounds pretty good, but for all the people who use Android OS in the world, that's actually tens of millions of people. Right, that's very, very bad. Right? So tens of millions of people are still not happy with it. Right. So what do? They basically look at this using the camera to observe the brightness level. Right. There's another person essentially. This is where the data is actually kind of puzzling. Right. So the user, we call her Mrs. Optimizer because she wanted to optimize something. We don't know what she's optimizing, right? So she basically uses this adjust the screen brightness in a very interesting way, right? So it actually goes. Sometimes she will adjust it brighter than what is recommended, and sometimes she will adjust lower than is recommended. This is sort of the average, right? This line here, right? So now this actually is interesting, right? So basically at the same brightness, right? Basically here, if you actually draw a vertical line here, at the same brightness, sometimes you will adjust it the brighter and sometimes you will adjust dimmer. Why? Okay, so the people at engineer Google are trying to figure out, wow, what kind of feature can we extract to help me? Remember feature, right? Features are information that you derive. Right? Maybe it's because sometimes you have glare, right? So maybe if you have glare and no glare, then they will actually look differently. So basically, they find a way to actually detect this camera, using the camera to detect whether you have direct incident lights using the backward camera, the camera that's facing you, right? They determine whether you have direct light hitting on you or you just have diffuse ambient lights hitting on you, right? And if you actually do this and you actually plot the data, right? The blue actually is the direct light, and the pink one is the diffuse light. Guess what? It looks somewhat like this. So it's actually not telling you anything. Sometimes even at the with the direct light, sometimes they actually turn it brighter, sometimes they turn it dimmer. Right? With diffuse light, sometimes you turn it brighter, sometimes you turn it dimmer. That doesn't explain the behavior, right? And sometimes they wonder, right? Is it a difference between the indoor and outdoor? Right? So they can actually use, for example, the spectral properties of the lights that they actually can detect, right? So remember, these are very sophisticated features, right? To take a camera and actually look at the environment and detect the spectral composition of the lights around, right? That's actually involve a lot of science, right? So basically, they are able to determine that natural lights have these kind of spectral feature, right? And artificial light have these kind of the spectrum of these lights look like this, right? So they're able to classify them. So they actually plotted the data again, so again, this natural light, sometimes sometimes in natural light, she'll adjust it brighter, sometimes she'll turn it dimmer. And sometimes in artificial light, she turns brighter and dimmer, right? So it's not because of that, right? Again, so what about well, maybe it's because it's spectrum, right? So these are what we call wideband spectrum, right? Like broadband or narrow spectrum, right? So these are narrow spectrum, so just different kinds of lights, right? So they look at all these are features that the engineer have to come up with, right? So they essentially, look at the data. Again, it's not telling you very much. Very often, so you can also tell that sometimes, it's just during broadband daylight, right, and also incandescent light. Sometimes you turn it brighter, sometimes you turn it dimmer. Likewise for the narrow band, right? So whether it's LED or iridescent incandescent light, fluorescent light, they still turn dimmer. So you can also tell that, she actually probably spent a lot of time outdoor because most of the time she just have broadband spectrum, right? So she probably don't use a lot of fluorescent or LED lights, So that tells you something, but doesn't solve the problem, okay? So what do you think is happening here? Huh? Yeah, it turns out that, it's the battery, okay? Okay, so, so this device actually have a lot of sensors, okay? It has information about the battery, right? Nobody thought of using that data, right? So they basically created another feature, right? When the battery is more than 30% full and the battery is less than 30% full, that's a feature, right? That's information, right? Based on the data that you measure directly on the phone, the battery level, okay? Okay, so that's a feature. Using that feature, basically they can say, oh, now it's very consistent, right? Every time the battery is less than, more than 30%, she's not afraid to turn the brightness up high, right? But every time the battery is less than 30%, she's very battery conscious. She wants to save battery, and so you actually turn the dimmer, okay? So very telling, right? So this is one example of how a simple feature, right? This brightness, screen brightness, right? Which you could easily turn up and down, right? But it's something that you have to do, right? You could actually turn it into an AI feature, right? So yeah, so now basically if you use a fit a 2-point spline with two options, right? Two kind of model, one for, now it is exactly 5 p.m. If you give me 7 more minutes, I'll finish, okay? So now, you have you essentially have two models, right? One for low battery and one for normal battery, right? And then now you actually can account for 99% of the human behavior. Now that's really good. That's very good, right? So now, basically, this is actually built into most Android system, right? I'm sure Apple iOS have similar kind of model as well, right? Basically, it's able to adjust brightness for you, okay? So how do you turn any AI, turn any kind of feature into AI, right? So this is a toy example, right? So suppose you come into your office. The first thing you do is to turn on the lights. Next thing you do is to turn on your computer. Next thing you do is you fire your email program, okay? These things are things that you do every single day, right? So wouldn't it be good to automate it, right? So automating this is actually not hard, right? You could basically, essentially put a door ajar sensor, right? Every time you open the door, right, it sends a radio wave RF signal to turn on the lights, and maybe you can actually turn on there's an automatic kind of signal that actually turns on your Wi-Fi, your computer as well. And then you can all have a auto-run script that runs your email. Easily doable, right? Okay, so next time it comes in, light turns on automatically, right? And then, email runs perfectly, right? So you're happy. Until one day, you come in busy with your phone, right? And talking on the phone, right? Lights turn on, right? But then you don't want to be distracted by email, right? So when you actually come to your computer, you turn off the email program, right? Okay, so with just automation, it's not going to learn that when I'm on the phone, I don't want you to start the email, right? So now the question is, what can you do to actually determine whether he's actually using his phone? What can you do? You can actually see the status of his app, right, where he's actually using the phone. The phone is actually an app, right? On your smartphone. On your smartphone, the phone is actually an app, right? So you can actually see if that application is active, right? And see, so these user behavior data is actually the feedback. They actually tell you something, right? This actually, your phone activity status, right, is telling you something that you can actually feedback. And so whenever you come in, when the phone status is actually on, you're actually using your phone application, maybe you don't want to run the auto script, the auto run script that starts your email, right? So what about another scenario where it comes in with a hot coffee in a cold day, right? So light turns on, he's happy, but then he wants to enjoy his coffee without disruption, right? So he turns off his computer completely, right? So now this system needs to learn that when he's actually with the coffee, right, you probably should not even start the computer, right? So they're learning from behavior, right? So basically, so he can actually enjoy his coffee, without disruption from his computer, right? So again, this behavior data is a feedback, right? So how can you learn from that? What kind of data can you actually get to tell whether he's actually drinking a coffee or not? Yeah, you could use temperature in the room, right? Yeah, there's actually lots of data you could use, right? For example, you could use a camera, right? Do object detection, see if you have a coffee in his hand, right? You can even do like credit card data, right? To see, hey, did he actually just spend the credit card on a cafe, buying something, like a few minutes before he comes to the office, right? But maybe you're in Europe and you don't want to use people's credit card information, right? Then maybe you can actually use just temperature. Maybe he's only drinks coffee in a cold day, right? Then so all these are actually, I would say, a rudimentary model that actually would do a decent job. I mean, with more data and iterations, you can actually collect more data. Remember, more and more features will actually tell you more and more precisely whether he's actually having coffee or not. Like having any one feature, remember having that, if I only look at having a beak, right, I would get that Concorde jet wrong completely, right? Because that Concorde jet actually looks like he has a beak. Right? But if with the multiple feature, right, having all those features at the same time, right, would very precisely identify what that object is. And same thing here, right? If you have a lot of features, you would be able to identify very precisely whether he's actually having a coffee or not, okay? Okay, so how do you turn any feature into AI, right? Basically, you find a repetitive human task that you want to automate, right? Human don't want to do this dumb, repetitive task, right? So you find the task that you want to automate, and you collect enough data to build to model that human behavior, right? And then so building a good enough model, data scientists can help you do that, right? You don't need to do all the code, right? Unless you are a data scientist yourself. And you deploy this model, right? And you want to continuously, the important thing is you want to continuously collect feedback data so that you can actually refine this model, right? Data from these feedback data could be data directly from the user, right? Could be from the market, right? Our airline product is actually getting feedback constantly from the market. Did people buy at this one for the fare at this price? Did they not buy it at this price, right? We're constantly getting that feedback, okay? And you may need to extend your model, for example, use a more sophisticated model, right? So and then there's a whole lot of process in the model refinement process, right? What other data you may need, right? For example, right, you may need to know what the battery level of the phone is, right? Which in the case of Google, they happen to have it, right? If you don't have it, maybe you need to collect that, right? So, so if data doesn't exist, you need to collect it, right? And so use this data to help you extend your existing model so that they can model users' behavior completely, okay? Almost completely. So with that, you know how, you have the foundation of big data, right? You know how machine learning works. It's about generating, creating and engineering good features and doing some math to turn that into a model, right? And you know AI, now you even know how to turn any feature into AI. So with that, you get a PhD in artificial intelligence, okay? So. And please remember to sign in to the session and remember to rate it. Again, if I'm telling you something that you completely did not understand, let me know, because I want to know. Because this course is literally designed for people who have no technical background. A Berkeley professor challenged me to do that, and I hope I've done it. So you could tell me in the feedback if I have done so. Thank you. Yeah.